What if everything you've been told about reality was just the surface layer? What if the universe isn't just stranger than you imagine, but stranger than you can imagine? What if time doesn't flow, space isn't empty, and even your own thoughts aren't entirely yours? In this video, we're diving into the mind-bending scientific truths that feel like science fiction, but aren't. From galaxies fleeing faster than light, to the possibility that your reality is just a projection, these aren't wild theories. They're the latest frontiers of science quietly reshaping what we know about existence, consciousness, and ourselves. If you've ever stared at the night sky and wondered what's really out there, or if you've ever looked inward and questioned the stories your brain tells you, this journey is for you. Hit that like button, subscribe, and join us, because once you see reality through this lens, you can't unsee it. So, are you ready to question everything you thought you knew? Let's begin. You age faster at the top of a skyscraper than at the bottom. They told you time is constant, that every second ticks away identically, no matter where you stand. A comforting thought, simple, fair, the kind of rule that makes the universe feel tidy, predictable, safe. But nature rarely bows to our desire for simplicity. Beneath the familiar rhythms of our clocks, time itself bends and flexes, quietly betraying the illusion of uniformity. What we call a second is not a universal truth. It's a local experience, shaped by invisible forces we barely notice. Time, it turns out, answers not to us, but to gravity. The closer you are to a massive object, like the vast, indifferent mass of the earth beneath your feet, the slower time flows for you. Climb higher and you slip into a faster current of time. Subtle, relentless. This is not philosophy. This is physics. Einstein's general relativity revealed that mass doesn't just warp space, it warps time itself. And we, fragile creatures of flesh and thought, are caught in that warping every moment of our lives. Picture yourself standing at the base of a towering skyscraper, steel and glass stretching toward the sky, your feet planted firmly on the pavement. Above you, 100 floors higher, another person leans against a window, gazing at the same city beneath the same sun. To the human eye, to human perception, you are sharing the same moment, the same second. But reality is more subtle, more precise. Physics whispers otherwise. Up there, in that elevated perch, time moves faster. Not enough for you to see, not enough to feel, but enough for the universe to measure, enough for atomic clocks, humanity's most precise instruments, to detect. Take two identical clocks, place one on the ground floor, send the other to the top. After a day, a difference will emerge. Microscopic, yes, but real. The clock above will have ticked slightly ahead of its twin below. An infinitesimal lead, but a lead nonetheless. Over a human lifetime, this discrepancy remains small. Perhaps a few microseconds gained by living higher up. But in the relentless calculus of the cosmos, such differences matter. They accumulate. They shape the very structure of reality. The Global Positioning System, GPS, relies on this effect. Satellites orbiting thousands of kilometers above Earth experience weaker gravity, causing their onboard clocks to run faster than those on the ground. If this discrepancy weren't corrected, your phone's location services would be wildly inaccurate, drifting kilometers off course in a matter of minutes. To navigate our cities, we had to acknowledge the subtle warping of time itself. What once seemed a philosophical curiosity became a technological necessity. A quiet, constant reminder that the universe doesn't care how we think time should behave. But this phenomenon isn't reserved for satellites or skyscrapers. It permeates every aspect of our existence. Hike a mountain, and you age faster than your counterpart at sea level. Fly in an airplane, and time flows differently for you, however slightly. Even climbing a staircase shifts you into a subtly faster tempo of time's passage. We like to imagine time as a smooth, even river, flowing uniformly from past to future, but the truth is more complex. Time is a landscape, sculpted by mass and motion, a terrain of invisible hills and valleys. Every step upward, every gain in altitude, is a step into a slightly different flow of time. You are not moving through a flat dimension, but traversing a dynamic, textured field that responds to your position in the cosmos. And this realization cracks open a deeper question, one that unsettles our intuitions. If time flows differently, depending on where you are, what does that mean for the present? For now, can we truly say we share a universal moment? Einstein's theory shattered that illusion. There is no absolute now stretching across the universe, only local moments, personal slices of time shaped by where you stand and how fast you move. The person at the top of the skyscraper isn't just higher in space, they are slightly ahead in time. Their future arrives fractionally sooner. Their past recedes a little faster. Not because of magic, but because of gravity's subtle influence on the fabric of reality. For everyday life, these differences are negligible. They won't make you visibly older than someone a few meters below. You won't gain extra birthdays by living in a penthouse, but the principle is profound. It reveals that time is not a neutral backdrop, not a passive stage upon which events unfold. Time is active, responsive, a living fabric, stretching and contracting under the influence of mass and motion. You are not simply moving through time. Time is moving through you, flowing, bending, shifting in response to your position in the universe. Your experience of reality is uniquely yours, not just in thought, but in physics. Even on Earth, where gravity's grip is gentle compared to cosmic behemoths, this truth holds. The Haffel-Keating experiment famously demonstrated it in the 1970s. Atomic clocks flown aboard commercial airliners were compared to identical clocks left stationary on the ground. The results aligned perfectly with Einstein's predictions. Time's flow depends on altitude and velocity. What we once considered immutable was revealed as malleable, elastic, subject to the quiet influence of invisible forces. In more extreme environments, this effect becomes dramatically visible. Near a black hole, gravity's grip becomes so intense that time slows to a crawl. To a distant observer, an object falling toward a black hole appears to freeze at the event horizon, suspended in an eternal moment. The same physics that makes you age faster at the top of a skyscraper governs the flow of time near these cosmic giants. The difference is only a matter of scale. The principles remain unchanged. Every breath you take, every step you climb, subtly shifts your place in time's flow. You won't feel it, you won't see it, but the universe notices. It's not science fiction. It's the quiet, relentless reality of a universe far stranger than we once imagined. The ordinary act of ascending a flight of stairs becomes a journey through a slightly different slice of time. The familiar is laced with the extraordinary, hidden beneath layers of perception we rarely question. So next time you look up at a skyscraper, remember, someone above you is aging faster than you. Their time moves more quickly, not in a way that will change your life, but in a way that reveals the subtle complexity of the universe. You are a traveler across time's uneven terrain. Every heartbeat, every breath is a step across that invisible landscape. You are not simply existing within time. Time is interacting with you, responding to where you are, how fast you move, and how gravity holds you in its grasp. This is the quiet poetry of physics, to reveal that even the most mundane aspects of our lives, walking, flying, climbing, are touched by cosmic forces beyond our senses. That the fabric of time itself flexes around us, shaping each moment in ways we cannot feel, but must acknowledge. You are not merely a passenger on time's river. You are a participant in its flow, a shaper of its path. Time is not a given, it is a consequence, a reflection of your place in the universe. Every instant you live is uniquely yours, molded by the unseen hand of gravity, the invisible dance of space-time. And in this intricate, ever-shifting reality, you are both the observer and the observed. Time moves through you as much as you move through time. Some galaxies are moving away from us faster than light. They told you nothing can travel faster than light, that it's the ultimate speed limit of the universe, immutable, absolute, a cosmic boundary beyond which nothing can go. This comforts us, makes the chaos of space feel manageable. We like universes with rules, but the universe is not built for our comfort. Out beyond the Milky Way, entire galaxies are moving away from us faster than light. Right now, not someday, this moment. As you listen, islands of stars recede at impossible speeds. How? Because space itself is expanding, and space is not bound by the same rules as light or matter. Picture an ant crawling on a balloon. It moves slowly, limited by its legs. But if you inflate the balloon, the surface stretches, and distant ants drift apart, not by moving faster, but because the surface beneath them grows. The ants obey their limits. The balloon does not. The universe behaves the same. Galaxies are not racing through space faster than light. Space itself is stretching, pulling them away. This is the Hubble-Lemaitre law. The farther a galaxy, the faster it recedes. At vast distances, this rate surpasses light speed, not by breaking physics, but because space expands faster than light can bridge. It feels like a semantic trick, but it's not. Space is not a static stage. It's dynamic, elastic, alive in its own way. Light moves through space, but when space expands faster than light speed, no photon can cross that growing gap. Those galaxies vanish beyond a cosmic event horizon, not by motion, but by the universe's own expansion. This isn't future theory. It's now. Hubble and James Webb observe galaxies whose recessional velocities exceed light speed. We see their ancient light because expansion was slower billions of years ago, but their now will never reach us. They're slipping away, not from movement, but from cosmic geometry. This reveals something unsettling. The observable universe is shrinking, not in size, but in what we can access. Each second, more galaxies cross that unreachable boundary, their stories severed, not by destruction, but by space itself carrying them away. This is the effect of dark energy, the force accelerating cosmic expansion, making up nearly 70% of the universe's energy. Its nature remains a mystery, but its influence is undeniable. Space expands. The universe grows lonelier. In the far future, only our local group, Milky Way, Andromeda, and a few dwarfs, will remain bound together, floating in an ever-growing void. The night sky will empty, not because galaxies died, but because their light can no longer reach us. The observable universe will become a shrinking bubble of what we can see, even as the universe itself grows. This forces a re-evaluation of distance, separation, connection. Space isn't a passive container. It's active, mutable. Distance is not fixed, but fluid. Two galaxies, once linked by light, can become eternally severed. Not because they moved, but because space itself refused to stay still. And if space's expansion can erase connections on a cosmic scale, what does that mean for our notions of nearness, of belonging? Perhaps distance is a construct of perspective, not meters. What feels permanent is revealed as transient. The universe's behavior shows us that even the most basic concepts, distance, connection, even now, are fragile, flexible, and ever-changing. For now, we live in a rare window of visibility. The cosmic event horizon hasn't swallowed everything yet. Light from the Big Bang still whispers to our telescopes. Ancient galaxies still tell their stories. But this won't last. The horizon grows. Beyond it, galaxies will form, stars will ignite, life may even arise. But their light will never reach us, not because of technology, but because the universe itself denies it. Yet this isn't a tragedy, it's a humbling, a reminder that we are part of a dynamic, evolving cosmos. The same forces that carry galaxies away once forged stars, planets, and life. We are not separate from this expansion. We are shaped by it. Understanding that galaxies recede faster than light teaches us that the universe breathes, grows, evolves, not as a cold machine, but as a living entity. We are ants on the balloon, but also minds that perceive the balloon's stretch, reflecting on its meaning. The speed of light remains the limit for matter and information, but space itself has no such boundary. In that loophole, the universe reveals its true nature, not fixed, but fluid, not static, but ever-shifting. So when you look up at the stars, remember, some of the light you see is already ancient. Some is on its final journey to you. And some galaxies are slipping away, beyond light's reach, not by defying rules, but by following them in ways we're only beginning to understand. Your brain makes decisions before you're aware of them. You believe you're in charge of your words, of your movements, of your life. You imagine your thoughts leading to decisions, decisions leading to actions, all driven by a conscious self that's firmly in the driver's seat. But science, as it often does, has quietly revealed a more unsettling truth, one that feels like a betrayal, even as it explains so much of who you are. Your brain makes decisions before you're even aware of them. Not metaphorically, not symbolically, literally. It started with a simple experiment in the 1980s. Neuroscientist Benjamin Libet asked volunteers to flex their wrists whenever they felt like it. At the same time, he measured the electrical activity in their brains. The result? A spike, known as the readiness potential, would appear in their brains before they reported deciding to move, not milliseconds before. Sometimes up to half a second earlier. Their brains had already started the process. The body was preparing, and their conscious minds were still oblivious, about to take credit for something already in motion. At first, it seemed like a fluke, a lab trick, but over the years this phenomenon was tested, retested, refined. Modern experiments with brain scanners extended this window even further. Researchers could predict a person's decision up to 7 seconds before they reported making it. 7 seconds. Imagine that. By the time you feel like you're choosing, the machinery is already at work, quietly finalizing what you'll do. But what does this actually mean for you? Is your free will an illusion? Are you nothing more than a puppet, with your brain pulling the strings while you narrate the moves? The answer is complicated. Your conscious mind isn't the general barking orders. It's more like a press secretary giving interviews about decisions made in closed rooms. You explain, you justify, you feel responsible. But the decisions themselves often come from layers you can't see. Fast, efficient, automatic. Think about the last time you reached for your phone without thinking, or the moment you spoke words you instantly regretted. You didn't plan those actions. They surfaced, emerged, and only afterward did your conscious mind scramble to make sense of them. I was bored. I just reacted. It felt right. Convenient stories for choices already made. But this doesn't make you powerless. Quite the opposite. Because while you might not control every moment-to-moment impulse, you have incredible influence over the patterns your brain relies on. Your habits, your environment, the information you consume. These shape the unconscious processes that feed your so-called spontaneous decisions. It's like steering a massive ship. You can't change its direction in an instant, but with small, consistent adjustments, you can shift its course, over time, dramatically so. The key is realizing that most of your decisions are not made in the spotlight of awareness, but in the shadows of habit, association, and emotion. This is where practices like mindfulness become powerful, not because they stop the unconscious machinery, but because they make you aware of it. They give you a moment's pause between impulse and action, a chance to notice, to redirect. Imagine your brain as a vast, ancient forest. Paths have been worn into the ground by years of walking the same routes. Habits, beliefs, reactions. When a choice arises, your brain tends to follow the familiar trails. But you can plant new seeds. You can forge new paths. Slowly, repeatedly, until one day, those once difficult choices become the new defaults. You won't feel yourself deciding differently. You'll simply notice that you do. This is how real change happens. Not through sudden flashes of willpower, but through the quiet, persistent reprogramming of unconscious patterns. You sculpt the terrain your brain navigates, and over time, your choices reflect that new landscape. Still, the fact remains, in the moment of choice, your conscious self is rarely the first to act. The brain operates on predictive models, constantly calculating what's likely, what's safe, what's rewarding. This system is fast, efficient, essential for survival, but it comes at the cost of genuine deliberation. Yet, understanding this can also foster compassion for yourself, for others. The impulsive comment, the knee-jerk reaction, the regrettable habit, they all originate from this hidden machinery. It doesn't excuse them, but it explains them. And in that explanation lies the opportunity to change. Even the very act of reading this now, of reflecting on your own decision-making, is shaping future choices. You are nudging the probabilities, feeding the system new data, creating micro-adjustments that, over time, become macro shifts. You are not a slave to your brain's unconscious processes, but you are their product and their gardener. The illusion of immediate free will, the feeling that you're choosing in the very moment, is a necessary simplification. It keeps you functional. It gives you a narrative. But beneath that story, a far more complex, beautiful reality is unfolding. You are not a single decider. You are a layered dynamic process, a symphony of signals, habits, predictions, and reflections. And consciousness, it's not the conductor. It's the melody line that rises from the orchestra, shaped by every section, every instrument, every player. So the next time you feel yourself making a decision, pausing before you speak, reaching for a snack, choosing a path, remember, your brain was already at work, long before you arrived. And that's not an insult to your agency. It's an invitation to understand yourself, to shape yourself, to stop trying to control every thought and start cultivating the patterns that guide them. Because free will might not be the power to choose in every moment, but it is the power to influence who you become over time. And that, in the end, is the decision that matters most. You share 60% of your DNA with bananas. It sounds like a joke, doesn't it? A quirky little fact designed to make you smirk. You share 60% of your DNA with bananas. Cute, funny, almost absurd. But beneath that silly comparison lies a truth, far more profound than it first appears. Because this isn't just a random coincidence of molecular similarity. This is a quiet reminder of something far bigger, that life, in all its diversity, is built on a common blueprint. And that blueprint connects you, not metaphorically but literally, to every living thing around you. Even a banana. Let's be clear. When we say you share 60% of your DNA with a banana, it doesn't mean you're 60% banana. It means that about 60% of the genes coded in a banana's DNA have counterparts in your own, genes responsible for the most basic, fundamental processes that make life possible. Building proteins, regulating cell division, managing metabolism, repairing damage. These are ancient, universal functions, so crucial to survival that evolution has preserved them across hundreds of millions of years. Think of DNA as a language. Life speaks in the same alphabet: A, T, C, G, adenine, thymine, cytosine, guanine. 4 letters, endlessly rearranged. And yet, from these simple components, the script of existence is written. The fact that you and a banana share large sections of this script is not evidence of absurdity, it's evidence of unity, of shared ancestry, of the deep, ancient kinship that binds all living things. Long before humans walked the earth, long before mammals, long before even fish swam in oceans, there existed simple, single-celled organisms that carried these same genetic instructions. Over eons, those instructions diversified, specialized, branched out into the staggering variety of life we see today. But they never lost their roots. In every cell of your body, echoes of that ancient code persist, mutated, adapted, but recognizable. When scientists compare genomes, they aren't just tallying up identical sequences, they're looking at shared genes. Homologous regions that perform similar functions. Genes that regulate basic cellular processes are astonishingly conserved. Because when something works, evolution doesn't reinvent it, it refines, it reuses. The molecular machinery that helps a banana grow is, in many ways, the same machinery that helps you heal a wound, digest food, even grow fingernails. But why bananas? Why not oak trees or mushrooms? The truth is, you share a significant portion of your DNA with almost every form of life. About 85% with mice, 60% with chickens, 40–50% with fruit flies, even 25% with simple yeast. The banana comparison sticks because it's so delightfully incongruous. Bananas are soft, sweet, stationary. You are none of those things. And yet molecularly, you are distant cousins. This revelation reframes how we see life. We are not isolated, miracles. We are branches of the same sprawling tree. The genetic overlap with a banana is not a fluke, it's a fingerprint. Proof that life, for all its complexity, builds itself from shared parts. It's like looking under the hood of wildly different machines and realizing they all run on variations of the same ancient engine. And this forces us to confront a deeper question. If you and a banana share so much of the same genetic material, what really separates you? What is it that makes you human? The answer lies not in the genes themselves, but in how they're used. In regulation, expression, timing. Two organisms might share a gene, but how, when, and where that gene is activated can create staggering differences. Consider a symphony. Two pieces of music might use the same notes, the same instruments, but arranged differently. They evoke entirely different emotions. Your genome and a banana's are like that. Similar notes, vastly different melodies. What sets humans apart is not the uniqueness of our DNA, but the complexity of how it's orchestrated. The genes involved in brain development, in social behavior, in language, these are not exclusive to us. But in humans, their expression is tuned, layered, and amplified in ways that create the rich tapestry of human consciousness. Yet even here, humility is warranted, because the difference is one of degree, not kind. The building blocks remain the same. The shared code, the shared chemistry, the shared history. This realization doesn't diminish your humanity. It deepens it. It places you within a continuum of life rather than above it. You are not separate from nature. You are nature arranged in a different pattern, and there's a quiet beauty in that. To know that every breath you take, every heartbeat, every cellular repair is part of a process billions of years in the making. That the same biological logic that grows a banana's peel shapes the formation of your skin. That life itself is a story written in a shared language, with infinite variations. This perspective also challenges the human tendency to categorize life hierarchically, to see ourselves as the pinnacle of evolution. But evolution has no pinnacle, no goal. It is a process of adaptation to environment, a constant branching experiment. The fact that you and a banana share common genes doesn't make you less significant. It makes life more miraculous, that from the same molecular toolkit, nature has crafted beings as different as trees, whales, insects, and humans. It also fosters empathy. When you realize that every living thing carries echoes of the same genetic heritage, it becomes harder to view nature as separate, as other. The line between us and them blurs. You begin to see the kinship in the most unexpected places, in the resilience of plants, in the cooperative behavior of fungi, in the adaptability of microbes. The same genetic whispers guide them all. So next time you peel a banana, pause. Consider the molecular threads that connect you. The enzymes breaking down sugars in its flesh have analogues in your own digestive system. The cellular processes that allowed it to grow are cousins to the ones repairing your skin. You are, in a sense, collaborating in an ancient biological dance, one species nourishing another, one form of life sustaining another. This is not a poetic metaphor. It is molecular reality, and perhaps in this humble truth lies a profound lesson, that the grandeur of life is not in its divisions, but in its unity, that the wonder is not in how different we are from bananas, but in how much we share. The same code, the same chemistry, the same stardust origins. You are not 60% banana, but you are 100% life, and that is far more remarkable. The universe may be finite, but has no edge. Close your eyes and picture the universe. Go ahead. What do you see? Stars scattered across a dark canvas, maybe a spiraling galaxy, maybe a web of light stretching in all directions. But no matter how far you zoom out, no matter how vast you imagine it, there's always a lurking question. Where does it end? Is there an edge? A wall? A place where space itself just stops? Intuitively, we think there must be. Everything we've ever known has boundaries. Cities end. Countries have borders. Oceans meet shorelines. Even the planet itself, this blue marble we call home, is finite. A sphere floating in space. So surely, the universe must work the same way. Surely, if you went far enough, you'd hit something. A cosmic fence, a final barrier, the edge of existence. But physics tells a different story. A stranger, more elegant one. The universe may be finite in size, yet it has no edge, no outer wall, no boundary you could bump into. A finite universe without an edge. It sounds paradoxical, like saying a room has walls but no corners. But the solution lies not in space itself, but in how space is shaped. To understand this, think smaller. Picture the surface of the Earth. You know it's finite, you can travel around it, measure it, map it. Yet, you will never find an edge. You could walk, fly, sail endlessly, looping back to your starting point without ever encountering a cliff, where the planet ends. The Earth's surface is finite but unbounded. It curves back on itself. Its edge is an illusion born of limited perspective. Now, take that same principle and expand it to 3 dimensions. This is how cosmologists describe the fabric of space. The universe, at large scales, may curve in such a way that traveling in a straight line forever would eventually bring you back to where you started, though it would take an unfathomable amount of time, and the universe itself might expand in the meantime. But the key point remains: no edge, no outside, just more space bending back on itself. This is what scientists refer to as a closed universe, a cosmos with positive curvature, like a higher dimensional sphere. Mathematically, it's called a hypersphere, not something you can visualize easily, because our brains are wired for 3 spatial dimensions. But in higher dimensional geometry, this concept is perfectly consistent. The universe can be finite in volume, yet have no boundary. Alternatively, the universe might be flat or open, extending infinitely without looping back. Observations suggest that on large scales, the universe appears flat. But even then, there's no edge, no cosmic border, no place where space runs out. Instead, space simply continues, perhaps forever, or perhaps curving subtly in ways beyond our detection. This realization flips our intuitive sense of space on its head. We imagine the universe as floating inside something, but there is no outside of the universe. The universe isn't an object within a bigger container. Space itself is the stage, and there's no external vantage point from which to view it from the outside. Asking what's beyond the universe is like asking what's north of the North Pole. The question itself breaks down. And yet, the human mind struggles with this abstraction. Because we are creatures of edges, of beginnings and endings. We are used to containers, to boundaries, to lines that divide inside from outside. Our brains evolved to navigate landscapes with limits. So when we try to grasp an edgeless universe, it feels slippery, paradoxical. But that discomfort doesn't make it less real. The cosmic microwave background, the afterglow of the Big Bang, serves as a kind of horizon for us, a limit to how far we can see, determined not by the edge of space, but by the age of the universe and the speed of light. Beyond that, more universe likely exists. We simply can't observe it yet, or ever. This distinction is crucial. The observable universe is finite because light has only had 13.8 billion years to reach us. But the universe itself, what lies beyond our cosmic horizon, could be much larger, perhaps infinite, perhaps looping back on itself. But in no case does it involve a hard edge where reality ends. So what would happen if you could somehow travel fast enough, far enough? You wouldn't hit a wall. You wouldn't fall into a void. You'd simply keep going. Space itself might be expanding faster than you can chase, but conceptually, your journey would be endless in direction, even if finite in volume. This brings us to the idea of topology, the study of shapes and spaces at the most fundamental level. A donut, for example, is topologically different from a sphere. The universe's topology determines whether it loops back on itself, whether it's finite or infinite, whether it's a hypersphere or a flat plane. These are not just philosophical musings. They are questions scientists investigate through observations of cosmic background radiation, galaxy distributions, and gravitational waves. But why does this matter to you? Because it reshapes how you think about existence itself. An edgeless, finite universe challenges the instinct to see reality as something boxed in, limited, containable. It suggests that reality doesn't need an outside to exist. That being is not dependent on contrast. You are not standing inside a cosmic aquarium. You are part of the fabric itself, moving within it, shaped by it, never separated from it. And perhaps this idea mirrors something deeper in human experience. The search for boundaries is not just about space. It's about identity, about wanting to know where I end and the world begins. But just as the universe has no edge, perhaps the boundaries of self are less rigid than we think. You are not isolated from reality. You are reality, aware of itself, stitched from the same fabric, playing out the same physics. So next time you look up at the night sky, try to resist the urge to imagine an invisible wall marking the end of it all. Instead, see it for what it is, an endless continuum, a reality that bends, curves, expands, but never ends. A universe that may be finite in measure, but infinite in connection, edgeless, boundless, alive. The universe has no fence, no outside, only more universe, and you are part of it. You could fit all humans into a sugar cube. It sounds like clickbait, a quirky fact to drop at a party. Hey, did you know you could fit all of humanity into a sugar cube? People laugh. They imagine miniature people squeezed like sardines, cartoonish and absurd. But what this statement really reveals isn't a joke. It's a window into a mind-bending truth about reality, about you, about matter itself. Because behind this casual one-liner is one of the most humbling facts of existence. You, me, everyone you've ever known are mostly empty space. Let's break this down. Your body feels solid. Your chair feels solid. The ground beneath you seems utterly reliable, but that's an illusion born of scale. On the atomic level, things are very different. Atoms are not little marbles packed tightly together. They're mostly vast, empty space. Imagine an atom scaled up to the size of a sports stadium. The nucleus, the dense core of protons and neutrons, would be no bigger than a marble at the center. The electrons would be tiny specks whizzing around near the stadium's edge. And everything else? Empty. Nothing. A cavernous void. The solidity you experience comes not from matter touching matter, but from electromagnetic forces. The reason your hand doesn't pass through your desk isn't because the atoms are physically stacked like bricks. It's because the negatively charged electrons in your hand repel the negatively charged electrons in the desk. A force field, an invisible barrier of repulsion. That's what you're feeling when you press your palm against a wall. Electromagnetic resistance between clouds of mostly empty atoms. Now, take this to its logical extreme. If you could somehow remove all the empty space from every atom in the human body, compressing the matter down to its pure, dense nucleus, you would be left with something unimaginably small. If you did this for the entire human population, about 8 billion people, you could compress all that nuclear matter into a single object the size of a sugar cube. Not figuratively. Literally, all of humanity, every bone, every organ, every drop of blood, reduced to a dense lump of pure atomic nuclei, sitting quietly on your kitchen counter. To understand why this is possible, you need to grasp just how much of an atom's volume is empty. The nucleus accounts for roughly 1/100,000th of the atom's diameter. The rest is just void. So when you think of your body's volume, what you're really imagining is a ghostly structure held together by forces, not by solid matter. The reality is that your body, your house, your planet, even this entire universe, is mostly emptiness, organized by rules of interaction, The density of that sugar cube of humanity would be staggering. A single teaspoon of neutron star material, matter compressed to nuclear density, would weigh about 6 billion tons. This is because in neutron stars, the same principle applies. Vast amounts of matter are collapsed into an incredibly small volume, with all the empty space between atomic nuclei removed. That sugar cube of humanity would have a comparable density, a miniature echo of the crushing forces inside a dying star. But let's be clear, this doesn't make you insignificant. On the contrary, it reveals something profound about the nature of existence. That structure, not substance, is what defines reality. That form arises from forces, from relationships, from fields of interaction. Not from sheer mass. You are not a solid block of matter. You are a delicate balance of energy, held together by invisible dances of attraction and repulsion. This also means that what we call matter is, in a sense, a localized expression of energy. Einstein's equation, EL-mc2, tells us that mass and energy are interchangeable. The mass of a proton is just the visible residue of the energy binding quarks together. The mass of an atom is mostly the binding energy of its components. You are, at your most fundamental level, a structured knot of energy patterns. So when you hear that humanity could fit into a sugar cube, you're not hearing about compression alone. You're hearing about the deceptive nature of scale, about how the macroscopic world you navigate daily, tables, buildings, oceans, is an emergent phenomenon built from nearly empty scaffolding. Matter isn't made of things, it's made of interactions. And yet those interactions give rise to everything, to the texture of your skin, to the taste of food, to the weight of your body, to the gravity that holds you to this planet. All of wet, emerging from fields of force, acting across what is by volume, emptiness. This fact should humble us, but it should also inspire awe, because it means that complexity, beauty, even consciousness itself, can arise not from dense substance, but from patterns within emptiness. The space between atoms is not wasted, it's essential. Without that space, electrons couldn't form stable orbits. Chemistry wouldn't happen. Life wouldn't happen. The empty space inside you is not a flaw. It's the very reason you exist. Now, let's step back. Why does this sugar cube fact resonate so much? Because it challenges a fundamental human instinct. The belief that size equals importance, that more mass means more meaning. But the universe doesn't care about such equations. The universe is built on structure, on relationships, on emergent complexity arising from surprisingly little. It's not about how much stuff you have, it's about how that stuff is arranged. A symphony is not more beautiful because it's louder. A painting is not more profound because it has more paint. Meaning arises from patterns, from relationships, from form. You are no different. So yes, you could fit all humans into a sugar cube, but that tiny cube would contain the memories of billions, the laughter, the grief, the dreams of an entire species. It would hold the stories of civilizations, the warmth of love, the pain of loss, the spark of curiosity. Compressed beyond recognition, yet still a record of everything we've been. It's a poetic reminder that scale is deceiving, that small does not mean insignificant, that the vastness of space, the emptiness within matter, does not diminish value. It creates the conditions for it. So next time you hold a sugar cube between your fingers, pause. Imagine the weight of 8 billion lives compressed within it, not as a morbid thought experiment, but as a meditation on how reality works, on how the tiniest structures give rise to the grandest phenomena. And perhaps, in that moment, you'll feel just a little more connected to the invisible architecture of existence, to the delicate balance of forces that hold you and everything else together. You are mostly empty space, and that emptiness is exactly what makes you real. You are living in the past. You've never seen now. You think you're experiencing the present, this very moment, the breath you're taking, the words you're reading, the world unfolding in front of you. But you're not. You never have. In fact, everything you see, hear, touch, and feel is already history. You are living in a delayed broadcast of reality, a fraction of a second behind the actual event, always late, always lagging. You've never seen now. It feels wrong, doesn't it? How can this be true? You blink, you clap your hands, you snap your fingers, and it all feels instant, immediate. But beneath that illusion, your brain is working furiously, desperately trying to synchronize a chaotic flood of information into something coherent. And that takes time, more time than you think. Let's start with the basics. Light travels fast, about 300,000 kilometers per second, but it's not instantaneous. When you look up at the night sky, you're seeing stars as they were years, even millions of years ago. The moon you gaze at is 1 1/3 seconds old. Even the sun's light takes 8 minutes to reach you. So right there, on a cosmic scale, you're always looking into the past. But this isn't just an astronomical quirk. It happens all around you, constantly, even here, even now. When you see someone standing across the street, the light bouncing off their face takes a few nanoseconds to reach your eyes. Insignificant, you think. Too small to matter. But then consider what happens next. Your eyes convert that light into electrical signals. Those signals travel along the optic nerve, reaching the visual cortex at the back of your brain. There, complex neural circuits process edges, colors, motion, depth. But vision doesn't work in isolation. Your brain integrates sound, touch, balance, combining it all into a seamless experience of now. Except, it's not seamless. It's stitched together, edited like a movie, with delays of 80 to 100 milliseconds. That's a tenth of a second, a blink of time. Yet within that blink, your brain is buffering reality, creating a best-guess version of the present. You never see the world as it is, you see it as it was, moments ago. Why does this happen? Because your brain is a biological organ, not a perfect processor. Neurons need time to fire. Signals take time to travel. Different senses process at different speeds. Sound reaches your brain faster than touch. Vision lags behind both. To keep your experience unified, your brain has to wait, collecting all the inputs, aligning them, smoothing them into a story that makes sense. Like a conductor waiting for every musician to catch the beat before starting the symphony. This introduces a delay, a necessary one, and it means your perception of now is actually a reconstruction, not reality unfolding in real time, but a heavily edited, slightly outdated version. You're watching a mental live stream with a built-in lag, yet it doesn't feel like that. Because your brain is also predictive. It doesn't just passively receive data, it forecasts, anticipates, fills in gaps. This is why you can catch a ball, follow a conversation, navigate a busy street without ever noticing the delay. Your brain constantly predicts what should happen next, and when the actual sensory data arrives, it adjusts, corrects, smooths the seams. Most of the time, it's flawless, until it isn't. Ever watched a video where the sound is out of sync? Lips move, but the voice lags a beat behind. That uncomfortable dissonance is what your brain fights against every second of your life. It compensates so well, you rarely notice. But the truth remains. Your experience of reality is always slightly behind. Now, think about what this means. You have never seen your own face in real time. Every reflection, every video feed, even your own hand moving in front of your eyes, all of it is delayed by nanoseconds, milliseconds, fractions too small to notice but never zero. You've never truly met yourself in the present, and this goes deeper. Because perception isn't just delayed, it's also filtered. Your brain discards vast amounts of sensory data. You're not aware of the blood vessels in your eyes, the constant hum of your own nervous system, the detailed texture of the chair you're sitting on. Unless you focus on them, your reality is curated, simplified, streamlined for survival, not for truth. The illusion of now is a brilliant hack, a compromise between fidelity and function. A slight delay buys your brain time to process complex stimuli, to resolve ambiguities, to keep you oriented in a noisy, chaotic world. Without it, your senses would clash. Your experience would fragment. But does this mean free will is an illusion? If you're always reacting to a delayed version of reality, are your choices already outdated the moment you make them? In a sense, yes. Every movement you make is based on information that's slightly old, yet your brain's predictive powers blur the line. By anticipating outcomes, you act with an uncanny sense of immediacy, even though you're technically behind. Athletes, musicians, drivers, all rely on this predictive processing. They don't wait for the present to arrive. They lean forward, into the future, riding the wave of expectation, adjusting on the fly. You do this too, every time you reach to catch a falling object or finish someone's sentence. Your brain isn't just a receiver, it's a forecaster, and yet philosophically, the implications are profound. The now you experience is a story your brain tells you, reconstructed from slightly stale data, patched with predictions, delivered with a smooth confidence that belies its latency. You never experience the immediate present. You never can. Your consciousness is always catching up. But perhaps this isn't a flaw. Perhaps it's a feature. A reminder that reality, as we perceive it, is not an objective stream, but a subjective creation, a collaboration between the external world and your brain's best interpretation of it. You are not a passive observer. You are an active participant in the making of now. So the next time you glance at your reflection, feel the breeze on your face. Hear the rustle of leaves. Remember, you are witnessing the past. The immediate past, yes, but the past nonetheless. You have never seen the present as it truly is. And yet, life unfolds perfectly, beautifully, within that gap. The lag between reality and perception doesn't disconnect you from the world. It connects you more deeply. It shows you that experience itself is a living process. Fluid, dynamic, always just slightly behind, yet always moving forward. You've never seen now, but you've always been part of it. Matter and antimatter should have cancelled each other. Imagine this. The universe blinks into existence with a burst of unimaginable energy. In the first fraction of a second, the cosmos is a seething soup of particles, pure chaos, pure potential. And then, as the universe cools, something peculiar happens. Out of that energy, particles of matter emerge, electrons, protons, neutrons. But alongside them, their mirror opposites are born. Antimatter. For every electron, an anti-electron. For every proton, an antiproton. Identical in mass. Opposite in charge. Perfect cosmic twins. And here's the catch. When matter and antimatter meet, they annihilate. Gone. Obliterated in a flash of pure energy. Poof. So, by all logic, by all known laws of physics, the early universe should have produced equal amounts of matter and antimatter. And if that were true, they should have met, collided, cancelled each other out. The universe should have ended before it began. Just radiation, no stars, no planets, no you. But look around. Clearly, something went wrong. Or, from our perspective, very right. Matter won. Somehow, inexplicably, there was a tiny excess of matter left over after the great cosmic showdown. For every billion pairs of matter and antimatter particles that annihilated each other, one lonely matter particle survived. 1 in a billion. That sliver of asymmetry is what built the universe. Every atom in your body, every mountain, every drop of water, every star, every galaxy, built from that tiny leftover. But why? Why did matter win? This is one of the greatest unsolved mysteries in physics. The universe plays by rules of symmetry, left and right, positive and negative, matter and antimatter. And yet here we are, existing in a cosmos made almost entirely of matter, while antimatter lingers only in laboratories and high-energy collisions. To understand why this is so strange, consider this. The equations of physics don't prefer matter over antimatter. They are blind to that difference. In fact, if you could flip the entire universe into its antimatter equivalent, the equations would run exactly the same. And yet, reality chose a side. Somehow, the universe broke symmetry. Scientists call this baryon asymmetry, baryons being particles like protons and neutrons, the building blocks of matter. The question is, where did the imbalance come from? What tilted the scales in favor of matter? There are theories, hypotheses wrapped in elegant math. Some suggest that in the seething energy of the early universe, subtle differences in decay, rates between matter and antimatter emerged. Tiny violations of symmetry, called CP violations, observed in certain particle interactions hint at this possibility. But so far, these observed asymmetries are too small to account for the overwhelming dominance of matter. Others propose that during cosmic inflation, a rapid expansion right after the Big Bang, quantum fluctuations might have seeded regions with slightly more matter than antimatter, or that exotic particles we have yet to discover played a hidden role, tilting the cosmic balance. But none of these explanations are confirmed. The truth is, we don't know why the universe exists as it does. Why there's something instead of nothing. Why matter, not antimatter, built the stars and you. This mystery is not just academic. It strikes at the heart of existence. If the balance had tipped the other way, if antimatter had been the winner, the laws of physics suggest the universe would look identical, but made of antimatter. You would be composed of antiprotons, antineutrons, and positrons, the antimatter, equivalent of electrons. Chemistry would proceed the same. Life might have emerged. From the inside, you wouldn't notice the difference, but from the outside, contact with ordinary matter would be catastrophic. Mutual annihilation. The universe's choice of matter over antimatter wasn't inevitable. It was a cosmic coin flip, weighted by processes we don't yet understand. And yet, here you are. A product of that imbalance. A living monument to a 1 in a billion mismatch. There's something humbling in that. You exist, not because the universe is orderly, but because, somewhere in the depths of its fundamental processes, a tiny crack of imperfection slipped through. A flaw, a glitch, and that glitch became reality, became us. It also reshapes how we think about the normal and the exotic. We call matter normal because we're made of it. But in truth, matter's dominance is the anomaly. Antimatter is not rare because it's unnatural. It's rare because of a primordial accident we still can't explain. In particle accelerators, we create antimatter routinely. When high-energy particles collide, pairs of matter and antimatter spring into existence, only to annihilate moments later. This recreation of early universe conditions lets us study the delicate balance of forces that shaped everything, yet every experiment, every collision, brings us no closer to understanding why matter had that microscopic edge. And perhaps that's the lesson, that existence itself is fragile, contingent, that the fact you can breathe, think, love, and wonder is a byproduct of a cosmic imbalance that should never have happened, but did. The universe had no reason to favor matter, but it did. So next time you hold your hand up to the light, feel the warmth of the sun on your skin. Pause. Realize that every atom in your body is a survivor, a relic of that improbable victory. You are here because the universe, somehow, chose matter over antimatter, or perhaps because matter refused to be erased. And in that refusal, everything began. We might be living in a hologram. It sounds like science fiction, a clever thought experiment, something straight out of the Matrix, or a late-night conspiracy forum. The idea that your entire reality, the walls around you, the ground beneath, you, the sky above, your own body, is not what it seems. That, in fact, it might all be a projection, a hologram, not in the sense of shimmering 3D light shows, but in a deeper, more fundamental way, a way that challenges the very nature of space, time, and existence itself. But this isn't a wild fantasy. This is a serious scientific hypothesis with roots in some of the deepest mysteries of physics. And it begins, oddly enough, with black holes. In the 1970s, physicist Jacob Bekenstein made a startling observation. When you feed mass into a black hole, its surface area, not its volume, increases. Later, Stephen Hawking discovered that black holes radiate energy, now known as Hawking radiation, leading to the eventual evaporation of the black hole itself. But this raised a paradox. If information about what fell into a black hole is lost forever, it violates a fundamental principle of physics, that information cannot be destroyed. To resolve this, physicists proposed the holographic principle. Here's the basic idea. Everything that falls into a black hole leaves an imprint on its surface, its event horizon. Not as a 3D object, but as a 2D record, like a cosmic tattoo. This means that all the information about a 3D volume of space can be encoded on its 2D boundary. In other words, the three-dimensional interior of a black hole could be fully described by data imprinted on its two-dimensional surface. Now, here's where things get mind-bending. Physicist Leonard Susskind, building on this idea, suggested that the entire universe might function in a similar way. That our 3D reality could be a projection from information encoded on a distant, two-dimensional boundary of the cosmos. Not because we're living in a glitchy computer simulation, but because the fundamental physics of the universe might require it. Imagine a hologram on a credit card. The image looks three-dimensional, but all the information needed to create that image resides on a flat surface. The holographic principle proposes that the entire universe might operate on this principle. That space itself is emergent, a kind of illusion born from deeper, underlying information. But why would the universe do this? Why would reality behave like a hologram? The answer lies in quantum gravity. When physicists try to unify quantum mechanics and general relativity, the math gets messy. But if you model certain regions of space, notably the event horizons of black holes, as holographic surfaces, the equations suddenly make sense. The holographic principle isn't just a quirky idea. It's a mathematical tool that might resolve some of the thorniest problems in physics. In 1997, physicist Juan Maldacena proposed a concrete version of this principle, known as the ADAS-CFT correspondence. In this model, a universe with gravity, like ours, in a higher dimensional space, can be fully described by a quantum field theory without gravity in one fewer dimension. The physics on the boundary mirrors the physics inside, much like a hologram. Though this model involves a universe with a specific type of negative curvature, unlike our own, the principle might still apply in broader contexts. The implication is profound. What we perceive as here might actually be information encoded out there. Now, before you start feeling like you're trapped in a cosmic illusion, let's clarify what this doesn't mean. It doesn't mean that reality is fake, that you're living in a glitchy simulation run by some advanced alien species. The holographic principle doesn't suggest a programmer pressing buttons. Instead, it suggests that the fabric of reality is more subtle, more layered than our immediate senses reveal. That dimensions might be emergent properties, not fundamental ingredients. Think of temperature. On a molecular level, there is no temperature per se. There are only particles moving at various speeds. Temperature is an emergent property of their collective behavior. Similarly, space and even time might emerge from deeper, more fundamental structures that are not spatial or temporal themselves. But why does this matter? Why should you care if reality is holographic? Because it challenges the very notion of what it means to exist. If space and time are emergent, then our understanding of cause and effect, of distance, of locality, all need to be reconsidered. What we think of as here and now might be reflections of deeper, non-local processes. Your hand, the room you're in, the stars above, they might all be manifestations of information projected into your perceived space. It also suggests that reality is deeply interconnected. In a holographic universe, what happens over there is not truly separate from what happens here. The divisions we perceive might be artifacts of perspective, not fundamental barriers. This doesn't make your experiences less real. On the contrary, it reveals how extraordinary it is that conscious beings like you can emerge from these hidden structures. The illusion of space doesn't diminish its beauty, it enhances it. Like realizing a rainbow is an optical effect, yet marveling at its splendor nonetheless. Furthermore, the holographic principle might hold clues to unifying quantum mechanics and general relativity, two pillars of modern physics that so far have resisted full reconciliation. By rethinking space itself as emergent from information, we might bridge that gap. But let's bring this back to you. right now as you sit. Here, reading these words, your brain is assembling a model of the world. Photons hit your retina. Electrical signals fire through neurons, but what you experience, the colors, the shapes, the sense of space, is a constructed reality. A simulation, if you will, generated by your brain. Not because the world is fake, but because perception is inherently interpretive. In this way, your experience of reality is already holographic. Your brain takes two-dimensional data from your retinas and constructs a vivid, three-dimensional world. You are already living in a projection of sorts. The holographic principle simply extends this idea to the fabric of the universe itself. It whispers that perhaps the universe, too, is projecting a three-dimensional reality from a deeper, lower-dimensional truth. So, are you living in a hologram? Maybe not in the pop culture sense, but in a profound scientific sense, the answer might be yes. And if that's true, it doesn't make your life less meaningful. It makes it more miraculous. Because it means that out of fundamental information, abstract, non-spatial data, arises the richness of existence. Stars, galaxies, laughter, pain, music, love, all emerging from patterns on a cosmic screen. You are not an illusion. You are the song of the universe, resonating through the patterns of a deeper, hidden reality. A hologram, perhaps, but a living, breathing, thinking one. And that's more astonishing than any fiction. Time might be an illusion. You live by the clock. Minutes ticking by, days slipping into weeks, birthdays piling up like pages in a calendar you can't stop turning. Time feels real, solid, immutable. It orders your memories. It gives structure to your plans. But what if time, this thing you measure, chase, and fear, is not what it seems? What if time, as you experience it, is an illusion? That's not poetry, that's physics. At its core, time feels intuitive. Cause leads to effect. The past becomes the present, then fades into the future. But peel back the layers of this experience, and you find something strange. Physics doesn't need time the way you do. In fact, the deepest laws of nature work just fine without it. Start with the equations. Newton's laws, Maxwell's equations, Einstein's field equations, all are time-symmetric. They don't care whether time flows forward or backward. The math works either way. Nothing in the fundamental laws demands an arrow of time. Yet your experience insists otherwise. You remember the past, not the future. You grow older, not younger. You see eggs break but never unbreak. This is where entropy enters the story. The second law of thermodynamics states that in a closed system, entropy, the measure of disorder, tends to increase. Ice melts, smoke disperses, cards shuffled don't spontaneously restack themselves. This increase of entropy gives us the arrow of time. It's why we perceive a before and after. But entropy is not a fundamental force. It's a statistical tendency, a description of large numbers of particles behaving probabilistically. On the microscopic scale, the equations remain reversible. At the level of fundamental particles, processes don't distinguish between past and future. The arrow of time emerges from the collective behavior of countless particles, not from some cosmic metronome. In fact, some physicists argue that time itself might not be fundamental at all, that it's an emergent property, like temperature or pressure. No single molecule has a temperature. Temperature arises from the average motion of trillions of molecules. Similarly, time might arise from the relationships between states of the universe, not from a fundamental flow. This leads to a radical proposition that time, as you experience it, is not an intrinsic feature of the universe, but a cognitive construct. Your brain stitches together sensory inputs, memories, and anticipations into a narrative of now. But in the raw fabric of reality, there may be no preferred direction, no flowing river, just a static landscape of events, all existing equally. Einstein himself hinted at this. In a letter to the family of a deceased friend, he wrote, "For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. Relativity already showed us that simultaneity is relative. Two events that are simultaneous for one observer may not be for another, depending on their velocity and position in a gravitational field. Time dilates. Clocks tick differently depending on where they are and how they move. The now becomes fuzzy. But if time is relative, not absolute, what does that say about its fundamental existence? Some theories, like Julian Barber's timeless physics, propose that the universe consists of a vast configuration space, Platonia, where every possible arrangement of the universe exists simultaneously. Motion, change, time itself are illusions born from our consciousness moving through this configuration space. In this view, what you call the passage of time is simply the succession of different configurations your brain experiences. Quantum mechanics adds another twist. In certain interpretations, such as the Wheeler-DeWitt equation in quantum gravity, time doesn't appear at all. The equation that describes the universe is timeless. The universe just is, without a global clock ticking in the background. But your mind resists this, because you are built to experience change, to remember sequences, to plan futures. Your consciousness is wired for time, yet physics suggests that this wiring might be more about evolutionary utility than cosmic truth. Think of a film reel. The movie feels alive, flowing from scene to scene. But the reel itself is static. Each frame exists simultaneously. The motion arises from the way you project those frames, one after another. Reality might work the same way. All moments, past, present, future, could exist at once. Your experience of time passing might be a byproduct of how consciousness moves through this tapestry. This doesn't mean time is meaningless. It means that what you call time is a perspective, like standing on a mountain ridge and seeing the valley below. The landscape exists whether you move or not. Your journey gives it the illusion of progression. Similarly, your consciousness traverses configurations of reality, giving birth to the sense of time's passage. This idea is not just philosophical musing, it has practical implications. In cosmology, the problem of time is a major hurdle in reconciling quantum mechanics with general relativity. If time is emergent, it could reshape how we understand the birth of the universe, black holes, even consciousness itself. But let's bring this back to you. Every time you check your watch, you affirm time's grip on your life. Deadlines, aging, regret, hope. But beneath these human concerns lies a deeper truth. Time is not a river flowing past you. It is a dimension, much like space. You don't travel through it in the way you imagine. Instead, you are embedded within a block universe, a four-dimensional space-time structure where all events are laid out. In this view, your past still exists. So does your future. You simply experience one slice at a time. The passage of time is not the universe moving forward, but your consciousness updating its location in the block. This might sound cold, deterministic, but there's beauty in it too, because it means every moment is eternally real. The laughter of a loved one, the warmth of a summer afternoon, even your own future triumphs, they exist, in a sense, forever, not as fleeting sparks, but as eternal coordinates in the fabric of reality. So, is time an illusion? From your perspective, it feels undeniably real. But from the universe's perspective, it might be nothing more than an emergent property, a convenient approximation. A story you tell yourself to make sense of change. Yet that story gives life meaning. It allows you to grow, to learn, to hope. The illusion of time might not be a flaw. It might be a gift. Because in a timeless universe, you get to experience time, and that experience, however illusory, is what makes your life feel alive. Your gut bacteria can influence your mood. You think you're the one in charge, that your thoughts, your moods, your decisions all come from you, from the command center inside your skull. But what if I told you there's a vast invisible ecosystem inside your body quietly pulling strings? Not in a sci-fi alien parasite kind of way, in a real, biological, scientifically proven way. Because the truth is, trillions of microbes living in your gut are influencing your brain, your feelings, your anxiety, even your happiness. This isn't a metaphor. This is your gut-brain axis in action. Let's start with the basics. Right now, inside your intestines, there's an entire rainforest of bacteria, viruses, fungi, and archaea. Collectively, they're called your gut microbiome, and they outnumber your human cells by at least a factor of 1 to 1. Some estimates go even higher. In terms of genetic material, these microbes outgun you by a factor of 100. You are, by the numbers, more microbe than human. For years, we thought of these gut bacteria as freeloaders, or at best, helpful sidekicks aiding digestion. But research, over the last 2 decades, has revealed something astonishing. These tiny organisms don't just process food, they produce neurotransmitters, they modulate immune responses, they influence inflammation, and most importantly, they communicate directly with your brain. The gut-brain axis is the bidirectional highway connecting your digestive tract to your central nervous system. Through the vagus nerve, a massive information superhighway running. From your brainstem to your gut, signals travel back and forth, relaying updates about the state of your inner world. But it's not a one-way street. Your brain can affect gut function, and your gut microbiome can affect your brain's chemistry. For example, certain gut bacteria produce gamma-aminobutyric acid, GABA, a key neurotransmitter that calms neuronal excitability and reduces anxiety. Others influence serotonin production, often called the feel-good neurotransmitter. Astonishingly, about 90% of your body's serotonin is produced in the gut, not the brain. Gut microbes also modulate dopamine pathways, which affect motivation and reward. This microbial influence isn't subtle. Studies have shown that germ-free mice raised in sterile environments without any gut bacteria, display exaggerated stress responses and altered behaviors. When these mice are given microbiota transplants from normal mice, their stress responses normalize. In humans, the connection is more complex, but correlations are undeniable. Imbalances in gut bacteria, known as dysbiosis, have been linked to depression, anxiety, autism spectrum disorders, and even neurodegenerative diseases like Parkinson's. But how do microbes in your intestines influence your mood? The mechanisms are multifaceted. First, through chemical signaling. Gut bacteria produce short-chain fatty acids, neurotransmitters, and other metabolites that cross into the bloodstream and reach the brain. Second, through immune modulation. The gut microbiome influences systemic inflammation, a key factor in many mood disorders. Chronic low-grade inflammation is often observed in depression and anxiety. Third, through the vagus nerve itself, providing a direct neural pathway for gut-brain communication. This gut-brain dialogue shapes your emotional landscape in ways you're rarely conscious of. Ever had a gut feeling about something? That's not just a metaphor. Your gut's neural network, the enteric nervous system, is sometimes called the second brain. It operates semi-independently, processing signals and sending them back to the brain. The sensation of butterflies before a big presentation, the sinking feeling of dread in your stomach, the loss of appetite during grief. These are all visceral manifestations of this connection. Even your cravings are not entirely your own. Certain gut bacteria thrive on specific nutrients, like sugar or fats, and can influence your food preferences through reward pathways, subtly nudging you toward choices that benefit them, not necessarily you. In a way, your microbiome is lobbying for its own survival, and your mood is part of the bargaining chip. But here's the empowering part. The gut microbiome is not a static entity. It's dynamic, malleable. What you eat, how you sleep, your stress levels, medications, all shape this internal ecosystem. Diets rich in fiber, fermented foods, and diverse plant matter nourish beneficial bacteria. Probiotics and prebiotics can help restore balance. Conversely, processed foods, excessive antibiotics, and chronic stress can decimate microbial diversity, tipping the scales toward dysbiosis. Understanding this gives you agency. You might not control every mood swing, but you can influence the terrain on which your emotional life plays out. Cultivating a healthy gut microbiome is not just about digestion, it's about mental resilience. But this connection runs even deeper. Evolutionarily, it makes sense. From the earliest stages of life, organisms developed symbiotic relationships with microbes. Over millions of years, this partnership became so intertwined that the boundary between self and other blurred. Your gut microbes co-evolved with you, shaping not just your physiology but your behavior. They are not invaders. They are co-authors of your experience. Some researchers even speculate that gut bacteria influence social behaviors. Certain species produce molecules that affect social bonding and stress responses. There are emerging studies exploring links between the microbiome and conditions like social anxiety and even empathy. The gut-brain connection is not just about individual mood, it's about how you relate to others. So when you feel irritable, anxious, or unmotivated, it's worth considering that your emotional state is not purely psychological, it's biological. A symphony of signals from neurons, hormones, immune cells, and yes, microbes. Mood is not a single chemical. It's an emergent property of a complex, dynamic system. You are not a mind trapped in a body. You are an ecosystem. This perspective is liberating. It dissolves the rigid mind-body duality. It shows you that mental health is physical health. That tending to your microbiome is not a fringe wellness trend, but a scientifically grounded approach to emotional well-being. So next time you find yourself in a bad mood, don't just ask what's on your mind. Ask what's going on in your gut. Because sometimes the answer isn't in your thoughts. It's in your microbes, and they've been talking to your brain all along. The universe might be just one of infinite universes. You've been taught to think of the universe as everything, the ultimate container, the sum total of space, time, matter, and energy. A vast, expanding bubble of existence, but still singular, the universe. One, all-encompassing. But what if that's wrong? What if this universe, the one with galaxies, stars, black holes, is just a drop in an infinite ocean of universes? What if reality is much bigger than we've dared to imagine? This is not idle speculation. It's the foundation of one of the most fascinating and controversial ideas in modern physics, the multiverse. At first, it sounds like science fiction, alternate universes, parallel realities, a cosmic copy of you living a different life. But, as strange as it seems, the multiverse emerges naturally from several well-respected scientific theories. Not as a desperate leap of imagination, but as a logical consequence of the mathematics that already describe our world. Let's start with inflation. In the earliest moments after the Big Bang, the universe underwent a period of rapid, exponential expansion, faster than the speed of light. This is known as cosmic inflation. It smoothed out the wrinkles in space-time, explaining why the universe looks so uniform on large scales. But inflation, according to most models, doesn't just happen once and stop. In many versions, it continues eternally in some regions, bubbling off pocket universes like foam in a boiling pot. These bubble universes are causally disconnected from each other. Each one may have its own laws of physics, its own constants, its own dimensions. Our observable universe would be just one such bubble, floating in an ever-expanding multiverse of possibilities. But it gets stranger. Quantum mechanics introduces another layer to the multiverse idea. The many worlds interpretation, proposed by Hugh Everett in 1957, suggests that every quantum event with multiple possible outcomes actually realizes all of them. The universe splits, creating parallel branches for every possibility. In one, you took that job. In another, you didn't. In one, Earth never formed. In another, life flourished earlier than here. The multiverse, in this view, is a constantly branching tree of realities, each as real as the one you're experiencing now. Even string theory, a leading candidate for a theory of everything, suggests a multiverse. String theory's equations allow for an enormous number of possible vacuum states, each corresponding to a different set of physical laws. The so-called string landscape could host up to 10,500 different universes. That's a 1 followed by 500 zeros. More universes than there are atoms in our observable cosmos. But what does this mean for you? It means that the universe might not be the ultimate stage. It might be just one room in an endless cosmic mansion, a single page in an infinite book, a fragment of a reality so vast our minds can barely scrape its surface. The implications are staggering. For one, it reframes the fine-tuning problem. Our universe seems oddly suited for life. The values of fundamental constants, gravity's strength, the charge of the electron, the cosmological constant, are set within narrow ranges that allow stars, planets, and ultimately life to exist. Why? In a multiverse, the answer might be simple. We live in one of the few universes where these values happen to permit life. No special reason, no design, just the inevitability of chance across infinite trials. But beyond physics, the multiverse challenges our sense of uniqueness. If countless versions of you exist elsewhere, each living slightly different lives, what does that say about identity, about choice? Are you still you if another version made different decisions? Does it diminish your significance or expand it? Philosophically, the multiverse can be unsettling. It whispers that reality is not a single coherent narrative, but an endless collection of possibilities. That certainty is an illusion born of limited perspective. But there's beauty in that too, because it means that existence itself is more generous than we imagined. That reality is not limited to what we can see, but teems with uncharted worlds, each playing out its own grand experiment. Of course, not all scientists embrace the multiverse. Some argue it's untestable, unscientific, that hypotheses without empirical evidence belong to philosophy, not physics. But others point out that many theories began as mathematical necessities before their predictions could be observed. Black holes, gravitational waves, quantum entanglement. What was once speculative became observable with better tools. We might not be able to detect other universes directly, but their fingerprints could exist in subtle anomalies, imprints in the cosmic microwave background, statistical irregularities in large-scale structures. Future observations might provide indirect clues, and yet, perhaps the most profound implication of the multiverse is not scientific, but existential. It suggests that reality is not defined by what you can experience, that beyond the edge of your observable universe, beyond the reach of your senses, lies an unbounded realm of existence, playing out stories you'll never witness, but which are no less real. It humbles you, and it elevates you. Because if the multiverse is real, then existence itself is vast enough to contain every possibility, every tragedy, every triumph, every version of you. You are not alone in the grand sense, not even unique. But you are here, experiencing this branch of reality, this moment. And that too is miraculous. The multiverse doesn't diminish your life's meaning. It multiplies it, because out of infinite possibilities, this, right now, is the one you're living, and that makes it priceless. The laws of physics are the same, but maybe not always. You grow up believing in rules. Gravity pulls things down. Light travels at a constant speed. Energy is conserved. The laws of physics are the backbone of reality, unchanging, universal, absolute. Whether you're on Earth, orbiting a distant star, or floating in the void between galaxies, these laws are supposed to hold. They are the scaffolding of existence, the silent agreement that keeps the cosmos predictable. But what if they aren't as immutable as we think? What if, across the vast expanse of space and time, the very laws that govern reality can shift? What if the universe isn't built on a single set of instructions, but on a patchwork of regions where the rules differ, subtly or perhaps profoundly? At first, this sounds like heresy. The scientific method thrives on the assumption that the laws of physics are the same everywhere. We build models, launch satellites, send probes across the solar system, all with the confidence that Newton's laws, Einstein's relativity, and quantum mechanics will behave consistently. And so far, they have. But when we look deeper, when we examine the universe with more sensitive instruments, we find hints, whispers, that suggest the possibility of variation. One of the key examples lies in the fine structure constant, often denoted as A. This dimensionless number governs the strength of the electromagnetic force. It influences how atoms hold together, how light interacts with matter, how chemistry unfolds. Its value is approximately 1/37, a figure so precise that small deviations could make stars unstable, atoms fall apart, or life as we know it impossible. For decades, physicists assumed A was constant throughout space and time, but studies of light from distant quasars, objects so far away that their light has traveled billions of years to reach us, suggest otherwise. Some observations indicate that the fine structure constant might vary ever so slightly across vast distances, not enough to unravel reality, but enough to challenge our assumptions. Is this variation real or an artifact of measurement? The jury is still out, but the implications are staggering. If physical constants can vary across space, then the laws of physics themselves might not be universally fixed. The universe, it seems, could be more like a quilt than a uniform fabric. Different patches with slightly different rules. And we, in our tiny cosmic neighborhood, might be experiencing just one local flavor of reality. String theory and cosmology offer further fuel for this possibility. In the landscape of string theory, there are countless possible vacuum states, configurations of space that correspond to different physical laws. Some might have stronger gravity. Others might have different numbers of spatial dimensions. The multiverse hypothesis suggests that every possible configuration is realized somewhere. We happen to live in one where the laws allow for complexity, for chemistry, for life. Even within our own universe, inflationary theory suggests that the early cosmos could have frozen in different physical constants in different regions. Like bubbles forming with slightly different properties, these regions would be causally disconnected, each with its own local physics. But even more intriguing is the idea that physical laws might not be immutable over time. As the universe expands and cools, it undergoes phase transitions, shifts in the fundamental nature of reality. Early in the universe's history, forces we now consider distinct, like electromagnetism and the weak nuclear force, were unified. Only as the universe cooled did these forces split into separate entities. In this sense, the laws of physics have already changed once. Could they change again? The idea of cosmic evolution doesn't just apply to stars and galaxies. It might apply to the very rules that govern them. But if the laws of physics can change, how can we trust science? How can we predict anything? The answer lies in scale. Locally, within our observable universe, the laws appear stable. Our measurements, from the tiniest quantum particles to the grand dance of galaxies, show remarkable consistency. The variations, if they exist, are so minute or so far removed that they don't disrupt the reality we experience. Yet, acknowledging the possibility of shifting physical laws expands our understanding of what a law really is. Perhaps laws are not divine edicts etched into the fabric of reality, but emergent properties, rules that arise from deeper underlying processes that themselves can evolve. It's like discovering that the rules of how water flows are not fundamental to water itself, but depend on temperature, pressure, and environment. In the same way, the laws of physics might be contingent, shaped by cosmic conditions, not absolute truths. This perspective reshapes how we see our place in the universe. We are accustomed to thinking of our physical laws as universal, but what if they are provincial? Local dialects of a broader cosmic language. Then, our understanding of reality becomes less about uncovering the one true law, and more about mapping the variations, understanding the conditions that give rise to different physical regimes. And yet, this idea is not chaotic. It doesn't suggest a universe without order. On the contrary, it reveals a deeper, more nuanced order. One where stability arises not from rigid, immutable laws, but from dynamic processes that maintain coherence across vast scales. You might wonder, if the laws of physics can change, could they change here? Could gravity weaken? Could light behave differently? In practical terms, such shifts would require conditions far beyond anything present in our cosmic neighborhood. But the fact that it's possible, at least in theory, reminds us of the delicate balance that makes our universe hospitable. Every breath you take, every atom in your body, exists within a framework of physical laws that, for now, remain steady. But somewhere out there, in the vastness beyond our reach, the rules might be different. And that's not a threat. It's a testament to the richness of existence. Because if the universe can write its own rules, then reality is not a fixed manuscript. It's a living story, one that evolves, adapts, surprises, and we are part of that story, bound by the laws of physics, yes, but also shaped by their mysteries. Falling into a black hole appears frozen to outsiders. Black holes are the universe's ultimate paradox. Born from the collapse of massive stars, they are objects of infinite density and zero volume, where gravity becomes so intense that not even light can escape. They distort space, warp time, and challenge everything we think we know about reality. But among their many strange behaviors, there's one phenomenon so counterintuitive, so mind-bending, it defies common sense. From an outside observer's perspective, anything falling into a black hole appears to freeze in time, forever suspended at the edge. It's not just a trick of the eye. It's not an optical illusion. It's physics. And it begins with Einstein's theory of general relativity. According to relativity, massive objects don't simply exert a gravitational pull. They bend the very fabric of space and time around them. The greater the mass, the greater the curvature. Black holes take this to the extreme. Their gravitational field is so intense that it creates a boundary known as the event horizon, the point of no return. Cross this threshold and escape becomes impossible. But here's where things get strange. Imagine a spaceship drifting toward a black hole. From the perspective of an astronaut inside, time seems to pass normally. Their heartbeat, their thoughts, their clocks all tick forward at a steady pace. They approach the event horizon, unaware that anything unusual is happening. But for an observer watching from a safe distance, say, orbiting far away, things look very different. As the spaceship nears the event horizon, the light it emits has to climb out of an increasingly steep gravitational well. This causes the light to stretch, its wavelength increasing, shifting toward the red end of the spectrum, a phenomenon known as gravitational redshift. The closer the ship gets to the horizon, the more extreme this redshift becomes. Its signals grow fainter, redder, more stretched, until they fade into invisibility. Simultaneously, time dilation kicks in. Gravity doesn't just warp space, it warps time itself. From the outside observer's perspective, the spaceship's clocks appear to slow down. Movements become sluggish. Each second aboard the ship takes longer and longer to be registered from afar. As the ship reaches the event horizon, this effect becomes infinite. To the distant observer, the ship never actually crosses the horizon. It appears frozen, suspended in time, hovering forever on the edge. This is not a trick of perspective. It's a consequence of how space-time behaves near extreme gravitational fields. From the outsider's frame of reference, the moment of crossing the event horizon is infinitely delayed. It's as if the universe itself conspires to prevent you from ever witnessing that final plunge. But from the astronaut's point of view, nothing special happens. They cross the event horizon in finite time, drifting ever closer to the singularity. Their fate is sealed, but to the rest of the universe, they seem stuck, locked in slow motion. Why does this happen? Because time is relative. In the presence of gravity, time flows differently for different observers. The stronger the gravitational field, the slower time passes relative to regions of weaker gravity. Near a black hole, this effect becomes extreme. The event horizon represents a kind of temporal boundary, not a physical wall, but a threshold where the difference in time flow becomes infinite when viewed from outside. But there's a bittersweet twist. As the light from the falling object becomes redshifted and dimmer, it also gets stretched out in time. Signals emitted just before crossing the horizon take longer and longer to reach the outside observer. Each successive photon carries the memory of the object's approach, but those memories are spread thinner and thinner across eternity. Eventually, the object's image fades into the cosmic background, not because it was destroyed there and then, but because the information about its position becomes infinitely diluted in time. It's a graceful disappearance, not a sudden one. This effect has profound implications for our understanding of information and black holes. The so-called information paradox arises because from the outside, it appears as if information about the falling object never truly disappears. It remains encoded, smeared across the event horizon, even as the object itself plunges inward. This observation aligns with the holographic principle, suggesting that all the information within a volume of space can be represented on its boundary. The frozen image of the object near the horizon becomes more than a curiosity. It becomes a clue to the deep structure of reality. But beyond the technicalities, there's something hauntingly poetic about this. The idea that you could fall into a black hole, never to be seen crossing the threshold, is a metaphor for the limits of perception. It's a reminder that reality is not absolute, that what you experience and what others observe can diverge in fundamental ways. That truth itself can be frame-dependent. You experience your own passage of time as continuous, flowing, but the universe might disagree. From afar, you might appear frozen, caught forever at the cusp of an invisible boundary, even as, subjectively, you move forward. And this isn't just a quirk of black holes. Time dilation, in milder forms, happens around Earth's gravity well, around massive stars, even in high-speed travel. GPS satellites orbiting Earth experience time differently than clocks on the ground, a fact engineers must correct for to keep your navigation accurate. But near a black hole, this difference becomes absolute. So next time you think of black holes as mere cosmic vacuum cleaners, remember, they are not just places where matter disappears. They are places where reality itself bends so far that the meaning of now, then, and never becomes fluid. Where the passage of time fractures into multiple perspectives. To fall into a black hole is to vanish slowly, gracefully, eternally, as seen by others. But from your own view, the journey continues, invisible. To the outside world, yet as real as ever. Vacuum of space boils with virtual particles. You hear the word vacuum and instantly think of emptiness, an infinite void where nothing stirs, no matter exists, no particles drift, no sounds echo. It's a vision of utter stillness, a cold, silent expanse stretching endlessly between stars, galaxies, and even atoms themselves. Space, in the common imagination, is the very definition of nothingness. But what if I told you that this picture is profoundly misleading? That the vacuum of space is not a barren wasteland, but a vibrant, restless ocean, a seething, boiling expanse alive with fleeting, ghostly entities that flicker into and out, of existence in the blink of an eye, so ephemeral that their presence seems to defy reality itself. These ephemeral phantoms are known as virtual particles, and they form the restless heartbeat of the quantum vacuum. Unlike the familiar particles that compose you and me, protons, electrons, photons, virtual particles inhabit a strange, ghostly realm. They do not obey the classical rules that govern ordinary matter. They emerge spontaneously from the deep, uncertainty woven into the fabric of quantum mechanics itself. At the heart of this strange behavior lies the Heisenberg uncertainty principle, a fundamental limit on what can be known simultaneously about a particle's energy and the precise moment it possesses that energy. This inherent fuzziness means that, for a fleeting instant, energy can fluctuate in what should be empty space, spawning pairs of particle and antiparticle that pop into existence together, exist just long enough to be detected as a blip in the quantum foam, then swiftly annihilate each other, vanishing before the universe even registers their presence. But these virtual particles, though brief in lifespan, leave very real footprints in the physical world. Take the Casimir effect, for example, a striking phenomenon first predicted in the mid-20th century and since experimentally verified. When two uncharged parallel metal plates are placed extremely close together in a vacuum, they mysteriously attract one another. This force is not due to any classical interaction, but arises from the difference in the quantum vacuum energy between the plates and outside them. Certain wavelengths of virtual particles simply cannot exist in the narrow gap between the plates, resulting in a subtle imbalance of pressure from the surrounding vacuum that nudges the plates together. Here, the very nothingness of space exerts a tangible force. Virtual particles also manifest themselves in the minute shifts in atomic spectra known as the Lamb shift, subtly altering the energy levels of electrons orbiting the nucleus of an atom. Their ceaseless dance beneath the surface affects matter's properties in ways invisible to the naked eye, but crucial to the stability and behavior of everything around us. Perhaps the most famous role of virtual particles plays out near the enigmatic event horizons of black holes. Hawking radiation, predicted by physicist Stephen Hawking in the 1970s, arises from the quantum activity of virtual particle pairs forming at the threshold of a black hole's boundary. Normally, these pairs annihilate each other almost immediately. Yet, if one particle crosses the event horizon while its partner escapes, that escaping particle becomes real, observed as radiation emitted by the black hole. Over unimaginably long timescales, this process causes black holes to slowly evaporate, shedding mass, driven by the restless froth of the quantum vacuum. But the influence of virtual particles extends far beyond exotic phenomena or theoretical curiosities. Quantum field theory, the deep framework underpinning all of modern physics, reveals that every point in space is not empty, but filled with fluctuating fields, an unceasing sea of potentiality from which particles arise as temporary excitations. Space, in this deepest sense, is never truly vacant. Instead, it is a dynamic, bubbling arena where energy condenses momentarily into particles before dissolving back into the vacuum in a continual cycle. These quantum fluctuations are not mere theoretical oddities. They play a fundamental role in the very fabric of reality. They influence the stability of atoms, the propagation of light, and the fundamental forces that bind the universe together. Without this ceaseless dance, the universe as we know it would be unrecognizable. To visualize this, imagine the surface of a calm lake. From a distance, it appears perfectly still and smooth, a mirror reflecting the sky. But as you draw closer, you notice the ripples, tiny waves, subtle disturbances dancing across the surface. Now shrink down to the scale of quantum fields, and you'll find that what once seemed like empty space is in fact more like a stormy ocean, roiling with virtual particles bubbling up and vanishing at every conceivable point in space. Yet here's the most perplexing part. If you calculated the energy density of this empty space as predicted by quantum field theory, you would arrive at a number so colossal it defies comprehension, some 10⁻20 times greater than what cosmological observations reveal. This discrepancy, known as the cosmological constant problem, is one of the greatest unsolved puzzles in physics today. Somehow, the staggering vacuum energy predicted by theory cancels out or hides itself, leaving behind only a faint residue that manifests as the mysterious dark energy accelerating the expansion of the universe. So virtual particles are far from trivial. They are deeply embedded in the cosmos's structure, influencing phenomena from the tiniest scales within atoms to the grand expansion of space-time itself. They are the invisible scaffolding upon which reality is built. And yet, even more mind-bending is this. Right now, in the very space between your eyes and the screen on which you read these words, virtual particles are continuously flashing into and out of existence. You do not see them, you do not feel them, but their restless activity shapes the world you inhabit. The vacuum is alive. It is vibrant. It is crowded. Not with matter or energy as you understand it, but with endless possibilities, ceaseless fluctuations, and whispers of creation at the edge of existence. Next time you picture space as a cold, empty void, remember, beneath its calm surface, the universe boils with invisible life. Reality's stillness is but an illusion, born of scale and perception. You are floating in the invisible tide of virtual particles, the ghostly heartbeat of the quantum vacuum. A vacuum can generate energy. You've been told that space is empty, that a vacuum is nothingness. But what if I told you that this nothingness could power the future? That in the vast, silent stretches between stars, in the empty space between atoms, lies an ocean of latent energy. Energy so immense, so fundamental, that if we could tap into it, it would dwarf every other power source humanity has ever dreamed of. Not nuclear, not fusion, not solar, vacuum energy, the energy of empty space itself. It sounds like alchemy, science fiction, the kind of concept whispered about in fringe circles. Yet beneath the outlandish claims, the physics is real. At the quantum level, emptiness is an illusion. The vacuum is not empty. It's a seething field of potential. And in theory, just theory for now, that potential can be harnessed. But to understand how, you first need to let go of your classical intuition. Forget the idea that space is a static backdrop, a silent stage on which particles dance. In modern physics, space is dynamic. It's a field, a canvas that ripples, fluctuates, and stores energy, even in its quietest state. This is where the concept of zero-point energy comes in. Zero-point energy is the lowest possible energy a quantum mechanical system can have. Even at absolute zero, where all thermal motion ceases, quantum fields retain a residual energy. This is not optional. It's a consequence of the Heisenberg uncertainty principle. You cannot simultaneously know a particle's position and momentum with perfect precision. This inherent uncertainty gives rise to fluctuations, minute, jittery motions that persist even in empty space. The vacuum, then, is not a void. It's the ground state of all quantum fields, humming with zero-point energy. And here's where things get interesting. In theory, this zero-point energy is enormous. Quantum electrodynamics, QED, suggests that every cubic centimeter of empty space contains vast amounts of energy. The exact number depends on where you cut off the calculations, a notorious problem, but estimates range from absurdly large to cosmically catastrophic. If all the zero-point energy in a single cubic meter of space could be extracted, it would be enough to vaporize entire planets. Of course, we don't observe this directly. Our universe isn't being torn apart by runaway vacuum energy. This discrepancy is part of the infamous cosmological constant problem, one of the biggest unsolved mysteries in physics. Somehow, this vast vacuum energy is either cancelled out, hidden, or balanced by other mechanisms, leaving only a small residual effect we observe as dark energy, the force accelerating the expansion of the universe. But the energy is still there. Potentially, this raises a provocative question. Can we tap into it? The Casimir effect is often cited as experimental proof that vacuum fluctuations can exert measurable forces. When two conductive plates are placed extremely close together in a vacuum, quantum fluctuations of the electromagnetic field are restricted between them. This creates a pressure imbalance, causing the plates to attract. It's a small force, but it's real. Measured. Verified. Could we scale this up? Could clever engineering, exotic materials, or future quantum technologies amplify such effects to extract usable energy? Enter speculative concepts like vacuum energy extraction devices. Theoretical models propose mechanisms by which energy differentials in the vacuum could be harnessed. Some suggest using dynamic Casimir effects, where rapidly moving boundaries can convert virtual particles into real photons, effectively extracting energy from the vacuum field. Others look to exotic states of matter, like Bose-Einstein condensates, which might interact with vacuum fluctuations in novel ways. In quantum field theory, interactions between matter and the vacuum are subtle and complex. It's conceivable that future advances in materials science could create systems where these interactions become a source of usable energy. But let's be clear, no one has built a vacuum energy engine. The laws of thermodynamics still reign. You can't get something for nothing. Any device claiming to extract vacuum energy must respect energy conservation and avoid perpetual motion schemes. But what we call vacuum energy isn't nothing. It's part of the universe's fundamental energy budget. If there are gradients, asymmetries, or exploitable phenomena, then energy transfer becomes a physical possibility, not magic, but mechanism. Some physicists speculate that the very expansion of the universe might represent a form of vacuum energy release. Dark energy, in this view, is vacuum energy influencing the large-scale dynamics of space-time. If so, then vacuum energy is already doing work on a cosmic scale, pushing galaxies apart, stretching space itself. The challenge is to find a way to harness such effects locally. Beyond mainstream physics, more speculative ideas emerge. Concepts like the zero-point energy drive or quantum vacuum plasma thrusters occasionally surface in advanced propulsion research. While most of these are highly controversial, they explore the tantalizing possibility that the fabric of space itself might offer a reactionless means of propulsion, using the quantum vacuum as a medium to generate thrust. Even NASA's EagleWorks team briefly investigated such concepts under names like the EM drive, though results remain inconclusive. The very notion forces us to confront whether momentum conservation can manifest differently when interacting with the vacuum field's complex properties. But perhaps the most mind-expanding aspect is this: if space itself contains latent energy, and if that energy can subtly influence matter, then the boundary between empty and full becomes philosophical. The vacuum becomes less like an absence and more like a hidden ocean beneath the surface of reality. An ocean with waves, currents, and, perhaps, tappable energy. In science fiction, devices like zero-point energy modules power interstellar ships, planetary shields, even entire civilizations. Shows like Stargate popularized the idea, but behind the fiction lies a seed of scientific plausibility. The energy is real. The challenge is engineering. Scaling the minute forces we observe into practical applications remains an open frontier. Yet, technological revolutions often arise from unexpected breakthroughs. Lasers were once a theoretical curiosity. So was nuclear fusion. Tapping vacuum energy might seem outlandish today, but if new physics emerges, if we discover ways to manipulate space-time or interact with quantum fields at finer scales, the dream could inch closer to reality. And it's not just about power plants or propulsion. Harnessing vacuum energy would revolutionize our understanding of reality itself. It would mean that nothingness is not passive, that the void is a reservoir of latent power. That space is not empty, but a dynamic partner in the dance of existence. It would also blur the line between technology and cosmology. Energy generation would no longer be about extracting fuel from matter, but about interacting with the fabric of reality itself. The implications for physics, philosophy, even spirituality would be profound, because to draw power from the vacuum is to engage with the universe's most fundamental layer, the zero point, the baseline hum of existence. It would be, in a very real sense, a conversation with the quantum heartbeat of the cosmos. So the next time you think of empty space as lifeless, think again. Because the vacuum is not void, it is potential. It is energy, waiting to be understood, and maybe, just maybe, one day, waiting to be harnessed. The universe had a beginning, but no time before it. You've heard the story 1,000 times. In the beginning, there was the Big Bang, an explosion, a moment of creation. The universe bursting forth from a singular point into the vast cosmos we see today. Simple, clean, intuitive. But the truth is far stranger, because while the universe had a beginning, what came before is not a question physics can answer. Because time itself began with the universe, there was no before. And that simple fact shatters everything you think you know about reality. Let's start with the question itself. What was there before the Big Bang? The problem is baked into the question. Before implies time, a sequence, a flow from one moment to the next. But the Big Bang wasn't an event that happened in time. It was the origin of time. There was no cosmic clock ticking away the seconds before it, because there was no clock at all. This isn't philosophical wordplay, it's physics. According to general relativity, space and time are not separate entities. They are two sides of the same coin, woven together into a four-dimensional fabric called space-time. Massive objects bend this fabric, creating what we experience as gravity. But here's the catch. Space-time is dynamic. It evolves, it curves, and it can begin. The Big Bang wasn't an explosion in space. It was the sudden appearance of space itself, expanding from an initial state of extreme density and temperature. Before this expansion, there was no where to be, no when to mark. The universe didn't expand into pre-existing space. Space expanded. Full stop. Einstein's equations describe how space-time behaves in the presence of energy and mass. But when you run these equations backward, tracing the universe's history, they point to a singularity, a point where densities become infinite and space-time curvature becomes extreme. But here's where things get subtle. This singularity is not part of the universe's timeline. It's a boundary, a limit. Asking what's before is like asking what's north of the North Pole. Imagine a sphere. Its surface has latitude and longitude, but the North Pole is a special point. You can go south from there, you can go east or west, but you can't go north of the North Pole. The question loses meaning. Similarly, time itself has a beginning point, the Big Bang. Not because something happened before, but because time itself emerges from the conditions of the universe. But what does it mean for time to begin? Surely something must have caused it, right? That's where quantum cosmology comes in. At the quantum scale, the classical picture of space-time breaks down. Near the Planck epoch, just 10 to 43 seconds after the Big Bang, quantum effects dominate. Space and time become fuzzy, probabilistic. The very notion of before and after becomes meaningless. One model, proposed by physicists James Hartle and Stephen Hawking, suggests that the universe has no boundary in imaginary time. Known as the no-boundary proposal, this idea posits that time, near the origin, behaves more like a spatial dimension. The universe is finite, but unbounded. Like the surface of a sphere, it has no edge. Time doesn't begin at a sharp point, but emerges smoothly from a timeless quantum state. In this view, the universe didn't come from nothing in the way we casually think of nothing. It emerged from a quantum vacuum, a state without classical space and time. Time itself is an emergent property arising from deeper, timeless laws. This is echoed in the Wheeler-DeWitt equation in quantum gravity, where time doesn't appear at all. The universe, in its most fundamental description, is timeless. What we perceive as the passage of time is an emergent phenomenon, arising from changes in configurations, relationships, and entropy. But if time began with the universe, what does that say about causality, about creation? In our everyday experience, every event has a cause. This follows from the fact that we live in time. Cause precedes effect. But when time itself is the thing being created, the notion of causality breaks down. There's no before to act as a cause. The universe didn't come into being in time. Time came into being with the universe. This challenges our intuition. We're used to thinking of time as a river flowing past us, but in physics, time is more like the landscape of the river itself. Events are not flowing in some absolute sense. Instead, the universe is a block of space-time, where past, present, and future coexist in a four-dimensional structure. Our perception of time's flow is a feature of consciousness, not of fundamental reality. So when you ask, what happened before the Big Bang? You're really asking what happened before time existed. And that's a self-contradictory question, like asking, what's further east than the East Pole? The question collapses under its own assumptions. This realization reshapes how we think about existence. The universe is not an object within time, it is time. Space and time are not containers that hold the universe. They are aspects of the universe itself. Asking what came before the Big Bang is like asking what's outside the surface of the Earth. There's no outside in the way you imagine. The Big Bang is not an event in time, it's the boundary of time. But this doesn't make the universe's origin less miraculous. In fact, it makes it more profound, because it means that reality, at its core, is not something that started in anything else. It's self-contained, self-defining. The laws of physics, the constants of nature, the fabric of space-time itself, all arise together from initial conditions that we're only beginning to understand. In speculative cosmology, there are ideas like eternal inflation and the multiverse, where bubble universes form within a larger inflating space. But even these models don't posit a before-time scenario for our observable universe. The concept of time might exist in the multiverse framework, but our universe's time begins with its own space-time fabric. Philosophically, this challenges the very idea of nothingness. We imagine nothing as empty space, silence, void. But in physics, nothing is a misnomer. Quantum vacuum states, potential fields, and the laws of physics themselves are not nothing. They are the structure from which space-time and matter emerge. The universe didn't come from nothing. It came from a state where nothing had a very different meaning. So what does this mean for you? It means that existence itself is not built upon a prior framework. Reality doesn't need an outside. Time doesn't need a before. You exist within a universe whose beginning is not a point in time, but the origin of time itself. It also means that questions like, why is there something rather than nothing, become more about the structure of the laws of physics than about classical cause and effect reasoning. The universe might not need an external reason to exist. Its existence could be a consequence of what's possible within the framework of quantum reality. And yet, this doesn't rob the universe of wonder. On the contrary, it deepens it. Because to live in a universe where time itself had a beginning is to live in a reality where existence and non-existence are not opposites, but phases. Where the flow of time, the progression of events, the very fabric of what you call now is a feature of an emergent, evolving cosmos. There was no before the Big Bang. Not because we lack information, but because before is a concept that only exists after. Sound can travel faster than light. You've been told that nothing can travel faster than light. That 299,792,458 meters per second is the ultimate speed limit of the universe. Immutable, absolute. The cosmic speed cap encoded in the very fabric of reality. And yet, buried beneath that certainty is a strange, little-known fact. Under the right conditions, sound, yes, sound, can outpace light. Not in empty space. Not in the vacuum where photons race unchallenged. But within certain materials, sound. Waves can propagate faster than light waves do through the same medium. It sounds impossible, a contradiction, but it's not. To understand this, you first need to shed a common misconception, that the speed of light is always the same, everywhere, no matter what. This is only partially true. The speed of light in a vacuum is indeed constant, but most of the universe is not a vacuum. It's filled with matter, air, water, glass, plasma, and in these materials, light slows down. This slowing happens because light, though massless, interacts with the charged particles in a medium. As a photon enters, it disturbs the electromagnetic fields of atoms, polarizing them, causing electrons to jiggle. These disturbances are re-radiated, passed along atom to atom, delaying the effective propagation of the light wave front. The photon isn't literally bouncing from atom to atom like a billiard ball. Rather, it's the collective electromagnetic response of the material that results in the appearance of light moving slower. This is why light moves slower in glass than in air, slower in water than in vacuum. Its speed in a medium is determined by the material's refractive index. For typical glass, this is around 1.5, meaning light slows to roughly 2/3 of its vacuum speed. But sound plays by different rules. Sound is a mechanical wave. It's not a self-propagating electromagnetic oscillation like light. It requires a medium, molecules bumping into each other, transferring momentum. The denser and more elastic the material, the faster these mechanical vibrations can propagate. In air, sound moves at a paltry 343 meters per second. In water, it jumps to 1,480 ms. In steel, it soars past 5,000 ms. In diamond, it reaches around 12,000 ms. The denser and stiffer the medium, the faster sound can travel through it. Here's the twist. While denser materials slow light dramatically, they often speed up sound. In materials like certain ultra-dense plasmas or exotic crystalline structures, it becomes possible for sound to outpace light, not in vacuum, but within that specific medium. Light slows down so much that sound wins the race. Does this mean Einstein was wrong? Does it violate relativity? Not at all. Relativity's speed limit applies to the transmission of information and causality in a vacuum. Nothing can carry usable information faster than light in empty space. But inside materials, both light and sound are subject to the quirks of their environment. The slowing of light is an emergent property of its interaction with matter. It doesn't contradict relativity because fundamentally, no, information is traveling faster than light in vacuum. In fact, the notion of speed becomes more nuanced when we distinguish between phase velocity and group velocity. Phase velocity refers to the speed at which the crests of a wave move. In some exotic materials, phase velocities can exceed the speed of light, or even become infinite. But this doesn't allow faster-than-light communication, because the actual signal or energy transfer depends on group velocity, the speed of the overall wave packet or pulse. Group velocity remains bound by relativistic limits, yet in certain media, the group velocity of sound can exceed the group velocity of light within that same medium. Sound outruns light locally. This happens because the mechanisms that slow light, electromagnetic interactions, are far more pronounced than those that govern mechanical vibrations. One particularly fascinating example involves ultra-dense nuclear matter. In neutron stars where matter is compressed to densities exceeding atomic nuclei, theoretical models suggest that certain sound waves, longitudinal pressure waves, can propagate at speeds approaching a significant fraction of light's vacuum speed. In these exotic conditions, sound waves could, in principle, surpass the speed of light within the same nuclear medium. Of course, neutron stars are not laboratories we can casually access, but the physics holds. Even here on Earth, materials like diamond, rhenium, and osmium exhibit exceptionally high sound velocities. As researchers develop metamaterials, engineered substances with custom electromagnetic properties, it's conceivable that we might design materials where light slows to a crawl while sound retains or even gains speed advantages. But what does this mean for us? It's a humbling reminder that speed is not a universal absolute in the simplistic sense. It's context-dependent, medium-dependent. Light is fastest in vacuum. Sound can be faster in dense, elastic media. The laws of physics are not being broken. Rather, they're being expressed in their full complexity. This phenomenon also draws an important distinction between fundamental speed limits and effective propagation speeds. When we say nothing can travel faster than light, we refer to the ultimate cosmic speed limit, the propagation of causality in space-time itself. But within media, where interactions slow down wave propagation, the playing field changes. Photons are delayed. Mechanical vibrations can surge ahead. A useful analogy is traffic flow. On an empty highway, a sports car can reach 300 km/h. But in a traffic jam, that same car might crawl at 10 km/h, while a bicyclist on a side path zips past at 25 km/h. The car's ultimate speed capability remains higher, but local conditions flip the outcome. Similarly, light's ultimate speed remains c in vacuum, but inside materials, its effective speed is reduced by interactions, giving sound a rare victory lap. This also connects to phenomena like Cherenkov radiation, the eerie blue glow seen in nuclear reactors. Here, charged particles travel through a medium faster than light does in that medium, emitting a shockwave of electromagnetic radiation. This is not faster than light travel in vacuum, but it vividly illustrates how context reshapes impossible into observed. So when you hear that sound can travel faster than light, the key is where? In diamond? Yes. In plasma? Under certain conditions? Yes. In vacuum? Never. The distinction is subtle but crucial. Beyond the physics, there's a philosophical elegance here. The fact that sound, so humble, so slow in air, can outpace light under the right circumstances, challenges our assumptions. It reminds us that reality is layered, that truths are often context-bound, that fastest is not an absolute title, but a situational advantage. For engineers and scientists, this opens doors to new technologies, hypersonic materials, ultra-efficient waveguides, novel acoustic systems, leveraging materials where sound supremacy offers unique benefits. For theoretical physicists, it reinforces the importance of distinguishing between phase velocity, group velocity, and signal velocity, each playing a different role in how we understand information propagation. But for you, sitting here, reading this, it's a profound lesson in humility. Nature doesn't care about our intuitions. Light is not always king. Sound is not always slow. Reality is more complex, more nuanced, and infinitely more interesting than our simple models suggest. And in that complexity, in that dance between waves and media, lies the true beauty of physics. Because sometimes, under the right conditions, the slow and humble sound outruns the cosmic sprinter we call light, and the universe simply smiles. There are more possible chess games than atoms. At first glance, chess seems simple. A board, 64 squares, 32 pieces. You know the rules. Pawns march forward, bishops slice diagonally, knights dance in L shapes. Two players, turn by turn, pushing pieces across a grid. And yet, buried beneath that simplicity lies a truth so staggering, so humbling, it reshapes how you think about complexity itself. The number of possible chess games exceeds the number of atoms in the observable universe. This is not poetic exaggeration, it's mathematics, pure combinatorics. But to grasp its weight, you need to see how quickly simplicity explodes into infinity. Let's start small. A chess game begins with 20 possible first moves for white. Pawns can advance 1 or 2 squares, 16 options. Knights can leap to 2 different squares each, 4 more options. Simple enough. But then black responds, another 20 possible replies. After just 2 plodding moves, the board has already branched into 400 possible positions. But it doesn't stop. After 3 moves apiece, there are nearly 121,000 unique board configurations. After 4 moves, close to 320 million. The numbers grow exponentially, not linearly. This is the heart of combinatorial explosion. Every decision spawns a tree of possibilities, and each branch gives rise to countless more. By the time you reach the 10th move, the number of possible unique games exceeds the number of stars in the Milky Way. After 20 moves, we're talking about numbers with more digits than there are grains of sand on every beach on Earth. Claude Shannon, the father of information theory, estimated the number of possible chess games at 10 to 120. That's a 1 followed by 120 zeros. For context, the estimated number of atoms in the observable universe is around 10 or 80. Think about that. A board with 64 squares and 32 pieces encodes more possibilities than the total number of fundamental building blocks of matter we can see. But why? How can a finite board with finite rules outpace the cosmos itself? The answer lies in the difference between size and complexity. The universe is vast, but in many ways its behaviors are constrained by physical laws, symmetry, conservation. Chess, while spatially limited, is a sandbox of decision-making, interaction, and freedom within boundaries. Each move is a choice. Each choice multiplies into futures, and those futures explode into new possibilities. It's not the board's size that matters. It's the branching tree of decisions. And this reveals something profound about complexity in general. Small systems with a few simple rules can generate landscapes of possibility that dwarf even the physical universe. But let's go deeper. When we say more chess games than atoms, what do we really mean? Is every possible sequence of moves a meaningful game? Are we counting nonsensical sequences where a player suicidally gives away their queen? Yes. The calculation includes every legal sequence, not necessarily every strategically sound one. But that distinction doesn't diminish the point. The rules allow it. The system contains it. Possibility does not require probability to be real. This invites a philosophical reflection. Complexity is not just about physical scale. It's about interaction, interdependency, feedback loops. A small system can contain infinite depth if its elements influence each other in intricate ways. Think of DNA. 4 nucleotides, A, T, C, G, combining into sequences that code for every living organism. The alphabet is tiny. The library it writes is infinite. Chess, too, is a language. The pieces are letters, the moves are words, and the games are stories, some short, some sprawling, some beautiful, some brutal, each unfolding along a path of choices. Now you might wonder, does this mean chess is infinite? No. The total number of possible games is finite, but so staggeringly large that, for all practical purposes, it feels infinite. Even if every human, who ever lived, played a unique game every second of their lives, the vast majority of possible games would remain unexplored. This dwarfs human imagination. It also humbles artificial intelligence. Even the most advanced chess engines don't solve chess by brute force calculating every possible future. They rely on heuristics, pruning unlikely branches, evaluating positions based on pattern recognition. Full enumeration of chess is computationally impossible with current technology. Not because it's infinite, but because it's combinatorially monstrous. And yet, humans play chess beautifully, not by seeing every possibility, but by navigating this ocean of potential through intuition, experience, creativity. We don't calculate 10, 120 moves. We feel patterns. We tell stories. Each game is a narrative of tension, sacrifice, victory, and defeat. In this way, chess becomes a mirror for reality itself. The universe, too, is combinatorially vast. Every interaction between particles, every fluctuation of quantum fields, spawns a tree of possibilities. And yet, order emerges. Structures form. Galaxies spin. Life evolves. Not because every possibility is explored, but because the rules guide certain patterns into being. This connection between the microcosm of the chessboard and the macrocosm of the universe is more than poetic. It's a reflection of how complexity arises from simplicity, how richness emerges from constraints. A chess game, in its branching potential, echoes the very processes of reality. Decisions, interactions, emergent patterns. The difference is scale, not principle, but there's another layer. When we say more chess games than atoms, we're comparing combinatorial possibility to physical quantity. But atoms are not the smallest units of information. In quantum physics, each particle's state, each quantum bit of spin, position, momentum, adds layers of complexity beyond mere counting. In this sense, the number of possible states of the universe itself far exceeds 10 to the power of 80 atoms. But the analogy holds. The point is not to equate chess games with atoms one-to-one. It's to illustrate how a simple, finite system can encode an ocean of complexity beyond our intuitive grasp. It's a lesson in humility. When you sit at a chessboard, you're not just playing a game. You're navigating a landscape more vast than the visible cosmos. Each move you make is a journey through a multiverse of possibilities, collapsing infinities into a single path. In this way, chess becomes a meditation on choice. Every pawn push, every sacrifice, every fork and pin mirrors the way we navigate life's decisions. Limited by time, by perspective, by cognitive resources, yet faced with an overwhelming branching tree of futures. We cannot calculate them all, but we move forward. And perhaps that's the deepest lesson chess teaches. That in a universe of staggering possibility, progress comes not from knowing every outcome, but from choosing, from committing, from embracing the flow of decisions, even in the face of uncertainty. So next time you hear someone say, chess is simple, smile. Because between those 64 squares lies a cosmos, a universe of possibility, a playground where more potential futures exist than atoms in the known universe. And every time you play, you're stepping into that infinity. 1 move at a time. Everything you see happened nanoseconds ago. You think you're seeing the present, that what unfolds before your eyes is reality as it is, right now, in this very instant. But you're not. You're seeing echoes, delayed reflections, light that left its source moments ago. Every sight, every color, every image you perceive is already in the past. Not by minutes, not by seconds, but by nanoseconds, microseconds, milliseconds. Depending on the distance and the scale, You are always looking back, always catching up. The truth is this: you have never, not once, seen the now. Because the universe doesn't allow you to. Light, for all its incredible speed, is not instantaneous. It takes time to travel. From the screen you're reading to your eyes. From the sun to the earth. From distant stars to our telescopes. This travel time, though minuscule on small scales, becomes significant as distance grows. But even here, in this room, across the space of mere centimeters, there's a delay, infinitesimally small, measured in nanoseconds, but real. Let's put this in perspective. Light travels at roughly 299,192,458 meters per second. That's nearly 300,000 kilometers every second, impossibly fast in human terms. Yet light still takes about 3.3 nanoseconds to cover just 1 meter. So when you look at an object a meter away, the image reaching your eyes left that object 3.3 nanoseconds ago. Not long, but not zero. Move further out. The moon is 384,400 kilometers away. The light from its surface takes about 1.3 seconds to reach Earth. Every time you gaze at the moon, you're seeing it as it was over a second in the past. The sun? 8 minutes and 20 seconds. The nearest star system, Alpha Centauri, about 4.3 years. Every observation you make is a glimpse into history, but it doesn't stop with light. Your perception is layered with delays. Neural processing adds its own lag. The photoreceptors in your retina convert light into electrical signals. Those signals traverse the optic nerve, pass through multiple layers of neural processing, and finally reach the visual cortex in the back of your brain. From there, further integration happens. Color, shape, motion, depth, all synthesized into a coherent image. This takes time, measurable time, tens to hundreds of milliseconds, depending on complexity. Your brain is a remarkable editor. It stitches these delays into a seamless experience of now. But this now is not the universe's now. It's a curated construct, a synchronized playback of events that already happened. You are always experiencing the world slightly behind reality. This isn't a flaw, it's a necessity. Your brain compensates by predicting. It anticipates the trajectory of moving objects. It fills in gaps. It corrects for delays. This predictive mechanism is why you can catch a ball, navigate traffic, or engage in conversation without constantly lagging behind. But prediction is not perception. You still react to information that is technically outdated. Consider this. When you watch a lightning strike, you see the flash before you hear the thunder. This is because sound travels slower than light. But even the light is late. The event already happened. You're just receiving the report after the fact. Even in intimate, close-range interactions, the delays persist. When you look into someone's eyes from a meter away, you're not seeing them as they are, but as they were 3.3 nanoseconds ago. Their current expression, their micro-movements, their subtle shifts, are already in the future relative to your perception. It seems absurd. After all, nanoseconds are negligible in daily life, but the principle holds. You never perceive the present as it is. You perceive a reconstruction of the past. On cosmic scales, this delay becomes profound. The Andromeda Galaxy, visible as a smudge in the night sky, is about 2.5 million light-years away. The photons hitting your retina tonight began their journey when early humans were first crafting stone tools. You are seeing ancient light, a ghost of Andromeda's past. If the galaxy vanished today, its image would linger in our skies for another 2.5 million years. This leads to a startling realization. The night sky is a time machine. Every star, every nebula, every galaxy is a window into the past. The further we look, the further back in time we see. The James Webb Space Telescope, peering into the deep infrared, captures images of galaxies as they were over 13 billion years ago, close to the dawn of the universe. But even here, on Earth, in your daily life, the same principle applies. The world you perceive is not the world as it is, but as it was. The difference is scale. In cosmic terms, the delay is dramatic. In human terms, it's imperceptible, but it's never zero. This raises philosophical questions. If we never experience the present directly, what does it mean to be in the moment? Are we perpetually out of sync with reality? Or is our perception of now simply a practical approximation, good enough for survival, but not aligned with fundamental physics? In physics, there's no universal now. Einstein's theory of relativity showed that simultaneity is relative. Two events that are simultaneous for one observer may not be for another, depending on their motion and gravitational field. Time is woven into space. Your now is a slice of space-time defined by your position and velocity. So in a profound sense, there is no global present, only local experiences of the past. Your consciousness strings these delayed inputs into a narrative of flowing time. But at the fundamental level, reality doesn't tick forward frame by frame. It exists as a continuum of events, some accessible to you, others not. This also means that our sensory limitations shape our understanding of reality. Our brains evolved to process the world within certain parameters. We're not designed to notice nanosecond delays. But technology has extended our reach. High-speed cameras reveal microseconds of events invisible to the naked eye. Particle accelerators observe interactions lasting femtoseconds. Atomic clocks measure time with mind-boggling precision, detecting discrepancies caused by mere centimeters of elevation in Earth's gravity well. And yet, even with all this technology, we remain anchored to our delayed perceptions. When you raise your hand, the photons reflecting off your skin take nanoseconds to reach your eyes. The electrical signals processing that information add milliseconds. By the time you perceive your hand moving, it has already moved. The action is in the past. Your experience is the playback. This also touches on free will. Neuroscientific studies suggest that decisions are initiated in the brain milliseconds before we become consciously aware of them. The readiness potential, measured in EEG studies, indicates that motor activity begins before subjective decision-making registers. Your conscious mind is informed of choices already set in motion. You live in a world of echoes, but does this diminish your agency? Not necessarily. It reveals that consciousness is less about real-time control and more about integrating delayed information into cohesive action. You are not a puppeteer yanking on strings in real time. You are a navigator of a slightly delayed, continuously updated reality. And yet, this delay does not make your experience less real. It makes it richer. Because within that buffer of nanoseconds and milliseconds lies the space for reflection, prediction, and imagination. Your brain doesn't merely record the past. It projects into the future, filling gaps, smoothing over discrepancies, creating a seamless narrative of being. In this way, the delay between reality and perception becomes a feature, not a bug. It grants you the illusion of fluid, continuous existence. It allows for coherent thought, for coordinated action, for meaningful interaction in a world where absolute simultaneity is unattainable. The fact that everything you see happened nanoseconds ago is not a failure of biology or physics. It's a testament to the intricate dance between perception and reality. A dance that allows conscious beings like you to exist in a universe where immediacy is an illusion, but connection remains real. So next time you look around, remember, you're not seeing the world as it is, you're seeing it as it was. But that's enough, because in those fleeting delays, life unfolds. The universe is getting colder while stars still burn. Out there, beyond the shimmer of stars and galaxies, the universe is dying. Slowly, quietly, not with a bang, but with a long, cold sigh. The night sky, though it dazzles with light, is a graveyard of ancient heat. Every photon that reaches you is a message from a hotter, more energetic past. Because despite the brilliance of suns, the universe is getting colder, relentlessly, irreversibly. This is not poetic exaggeration, it is thermodynamic certainty. To understand why, you need to revisit the beginning. In its infancy, the universe was a seething ocean of energy, hotter than any star, denser than any black hole, a plasma of particles and light, so dense that photons couldn't travel freely. They bounced and scattered, trapped in a fog of matter. But as space expanded, it cooled. After about 380,000 years, temperatures dropped enough for electrons and protons to combine into neutral atoms. This moment, recombination, released the photons now seen as the cosmic microwave background radiation. That glow, filling all of space, was once a brilliant, blinding white, but expansion stretches space itself, and with it stretches the wavelength of light. What was once a searing blaze has been redshifted into a faint, cold whisper. Today, the cosmic microwave background has a temperature of just 2.7 Kelvin. Barely. Above absolute zero, this relentless cooling continues. As the universe expands, the average energy density drops. The wavelengths of ancient photons stretch further. The overall temperature of space decreases. It's a slow process, imperceptible on human timescales, but inevitable. And yet, stars still burn. Suns blaze with nuclear fusion, forging heavier elements from hydrogen and helium. These stellar furnaces radiate heat and light, injecting energy into the cosmos. Locally, they create pockets of warmth, regions of high entropy production. But these are exceptions, fluctuations in an ocean of growing cold. The key to this paradox of burning stars in a cooling universe lies in understanding the difference between local entropy production and global thermodynamic evolution. Stars do not reverse cosmic cooling. They are engines of entropy increase. Through fusion, stars convert low-entropy fuel, hydrogen, into higher-entropy byproducts, helium, radiation, neutrinos. In doing so, they radiate energy into the cold vacuum. But this radiation does not heat the universe in the global sense. It merely disperses energy, spreading it thin across an ever-expanding canvas. Imagine a bonfire in a vast icy desert. The fire radiates heat, creating a local sphere of warmth. But beyond that sphere, the cold remains undisturbed. Worse, the fire consumes its own fuel. Over time, the warmth fades, the ashes cool, and the desert's cold triumphs. The universe is that desert. Stars are the fires. But there's a deeper reason why the universe's temperature keeps dropping. Cosmic expansion is not just about galaxies moving apart. Space itself is stretching. This expansion increases the distance between photons, diluting their energy. A photon's wavelength determines its energy. Longer wavelengths mean lower energy. As space expands, photon wavelengths stretch, reducing their energy. This is the essence of cosmological redshift. The universe's cooling is not because energy is disappearing, but because it's being spread thinner across an ever-growing expanse. Even the radiation from stars, once emitted, succumbs to this redshift. The visible light of a distant galaxy, over billions of years, is stretched into infrared, then into microwave, and eventually into radio wavelengths. Over cosmic timescales, even starlight fades into the cold. The second law of thermodynamics governs this progression. In any closed system, entropy, the measure of disorder, tends to increase. The universe, as far as we know, is a closed system. Over time, usable energy becomes less concentrated, less able to do work. Stars shine by burning through gradients, hot plasma against cold space. As the gradients diminish, so does the capacity for work. This is the long march toward thermodynamic equilibrium, heat death. But how can we reconcile this slow cosmic freezing with the abundance of burning stars? The answer lies in timescales. The universe is about 13.8 billion years old. Stars like our Sun have lifespans of about 10 billion years. Smaller stars, red dwarfs, can burn for trillions of years. On human scales, this feels eternal. But in cosmic terms, it's transient, a flicker in the dark. Stellar formation has already peaked. The golden age of starbirth occurred several billion years ago. Since then, the raw material, cold hydrogen gas, has been depleting. Galaxies have less fuel to form new stars. The universe is aging. In the far future, star formation will cease. Existing stars will exhaust their nuclear fuel. Massive stars will explode as supernovae, leaving neutron stars and black holes. Smaller stars will cool into white dwarfs, then into black dwarfs, cold, dark remnants. The the universe will become a gallery of stellar corpses. Black holes, too, are not eternal. Through Hawking radiation, they slowly evaporate, leaking energy into the void. But this process is unimaginably slow. A stellar mass black hole would take 10⁻⁻�67 years to evaporate. Yet, given enough time, even black holes will fade. And what remains then? A universe filled with thinly spread, low-energy photons. A sea of cold, dark matter. No stars, no black holes, just entropy maximized. Temperature asymptotically approaching absolute zero. The ultimate equilibrium. But equilibrium is not dynamic. It's not creative. It's stillness. In this bleak vision, called the heat death scenario, the universe doesn't end in a dramatic collapse or explosion. It simply fades into uniformity. A cold, dark expanse where no gradients exist. No work can be done, and time itself becomes irrelevant, as no events distinguish one moment from the next. And yet, even as we trace this long, cold future, the present still burns. Stars like our Sun convert millions of tons of hydrogen into helium every second. Their light travels across space, giving life to planets, warming worlds, igniting consciousness. Locally, the universe remains vibrant. Galaxies swirl, planets orbit, life evolves. This tension between the local and the global is a defining feature of our cosmos. Entropy increases globally, but locally, complexity flourishes. Stars are entropy engines. Life, too, is an entropy engine. We feed off energy gradients, sunlight, chemical potential to maintain order within ourselves, even as we contribute to the universe's overall disorder. This dance of order arising from disorder, of life thriving amid cosmic decay, is not a contradiction. It's thermodynamics at work. The existence of local pockets of low entropy, like stars and living beings, is a natural consequence of entropy increasing elsewhere. But the arrow of time points forward. The universe's fate is sealed not by any malevolent force, but by the inescapable mathematics of thermodynamics. Yet, knowing this, does it diminish the beauty of the night sky? Does the fact that every star is a temporary fire make its light less precious? Or does it make it more so? Every photon reaching your eyes is a triumph against entropy. A fleeting moment of order, blazing defiantly against the cold. You are alive, in a universe where stars still burn, where light still cuts through the dark, where gradients still exist and life still thrives. One day, that will no longer be true, but today, it is. And that makes this moment extraordinary. The universe is getting colder, but for now, it still shines. Dark energy gives empty space. Wait. We like to think of empty space as truly empty, a perfect void. No matter, no light, no sound. Just a black, infinite nothingness stretching between stars and galaxies. But this vision of space, beautiful in its simplicity, is a lie. Because empty space is not empty. It has weight, it has energy. And though it does not shine or burn, it dominates the fate of the cosmos. This invisible presence is what we call dark energy, a force so subtle, yet so vast, that it is accelerating the universe itself. But how can nothing have weight? To answer that, we must revisit our assumptions about nothing. In classical physics, empty space was treated as a passive backdrop, a stage upon which the play of particles and forces unfolded. Space was geometry, devoid of substance. But modern physics tells a different story. According to quantum field theory, space is not a mere void. It is a dynamic fabric, humming with zero-point fluctuations. Even in the absence of particles, quantum fields persist. Virtual particles pop in and out of existence. Energy exists even in the vacuum state, the lowest possible energy configuration. This zero-point energy gives empty space a kind of latent vitality. But dark energy is more than zero-point jitter. It's a pervasive, uniform energy field that exerts pressure on the universe itself. And its most astonishing property is this: it has negative pressure. In everyday experience, pressure works to compress. Pump up a tire, and air pushes outward against the rubber. But dark energy's negative pressure does the opposite. It pulls space outward, causing the universe's expansion to accelerate. This was not always known. For most of the 20th century, cosmologists believed that the universe's expansion, first discovered by Edwin Hubble in 1929, was slowing down due to gravity. The mass of galaxies, stars, gas, all pulling inward, trying to halt the outward rush born from the Big Bang. But in the late 1990s, observations of distant Type Ia supernovae revealed a shocking truth. These stellar explosions, serving as standard candles, allowed astronomers to measure cosmic distances with unprecedented precision. What they found was not a slowing universe, but one speeding up. Galaxies were not just receding, they were accelerating away from each other. This discovery upended cosmology. To account for this acceleration, a new component was needed in the cosmic inventory: dark energy. Today, dark energy is thought to constitute about 68% of the total energy content of the universe. Dark matter accounts for roughly 27%. The normal, matter that makes up stars, planets, and you, just 5%. Think about that. Everything we see, touch, and know is a rounding error in the universe's energy budget. But what exactly is dark energy? One hypothesis is that it is a property of space itself, a cosmological constant, as first proposed by Einstein. In this view, the energy density of space remains constant even as the universe expands. More space means more dark energy, maintaining a constant density. This is unlike matter or radiation, whose densities decrease as space stretches. Another possibility is that dark energy is dynamic, a field that evolves over time, akin to the inflaton field thought to drive cosmic inflation in the early universe. This model, known as quintessence, posits that dark energy's strength could vary across cosmic epochs. But regardless of its nature, dark energy's effect is undeniable. It gives empty space weight, not in the sense of traditional mass, but as a form of energy that curves space-time and drives cosmic expansion. Einstein's general relativity tells us that energy and mass are interchangeable. Energy curves space-time, dictating how objects move. Even the vacuum energy contributes to this curvature. Dark energy's negative pressure acts like an anti-gravity force, not by pushing objects apart directly, but by stretching the fabric of space itself. As space expands, more space comes into being. If dark energy's density remains constant, then the total amount of dark energy increases as the universe grows. This creates a feedback loop. Expansion creates more space, which holds more dark energy, which accelerates expansion further. But here's a subtlety. Dark energy does not act on local scales. Gravity still binds galaxies, solar systems, and atoms. The expansion driven by dark energy becomes significant only over vast intergalactic distances where gravity's grip weakens. This is why we don't see the Milky Way expanding or the Earth drifting away from the Sun. Dark energy's influence is real but diffuse, manifesting only across the immense canvas of the cosmos. Yet over time, its impact becomes profound. As dark energy drives the universe's acceleration, distant galaxies slip beyond our observable horizon. Light from these galaxies stretches into wavelengths so long that it can no longer reach us. The universe becomes lonelier. In the far future, only our local group of galaxies, gravitationally bound together, will remain visible. Beyond that, an expanding ocean of cold, empty space. This ultimate fate is sometimes called the Big Freeze, or heat death. Not because space itself freezes, but because the expansion dilutes matter and energy to the point of cosmic stillness. Temperature drops, star formation ceases, black holes evaporate, entropy reaches its maximum, and through it all, dark energy remains. But there's a paradox here. If dark energy is a property of space, why is its density so small? Quantum field theory predicts a vacuum energy density 120 orders of magnitude larger than what we observe. This discrepancy, known as the cosmological constant problem, is the biggest numerical mismatch in physics. Why is dark energy's effect so subtle, yet so decisive? Some theories propose that multiple universes exist, each with different values of vacuum energy. We happen to live in one where dark energy's strength permits the formation of galaxies, stars, and life. In other universes, dark energy might be so strong that cosmic expansion prevents structure from forming at all. This is the anthropic principle in action, a controversial but intriguing idea. Others search for new physics. Perhaps dark energy is not a cosmological constant, but the manifestation of deeper unknown fields. Perhaps modifications to general relativity on cosmic scales are needed. But even in the absence of definitive answers, the observation remains. Empty space has weight, it has energy, and it shapes the destiny of everything. This realization transforms our understanding of nothingness. The vacuum is not empty, it's a sea of latent energy, subtle yet dominant. What we perceive as empty space is the very substance through which the universe evolves. Philosophically, this challenges the boundary between something and nothing. If space itself carries energy, then emptiness becomes an active participant in cosmic evolution. The void is not absence but potential. It exerts influence without particles, without radiation, simply by existing. In a poetic sense, dark energy gives weight to the silence of the cosmos. It reminds us that absence can have presence, that stillness can have momentum, that the void is not passive, but alive with the quiet force that shapes galaxies and stretches the fabric of reality. As you look up at the night sky, understand that the darkness between stars is not empty. It's not dead space. It's not nothing. It is filled with the weight of dark energy, invisible, relentless, infinite, and it is pulling the universe apart. Black holes have infinite density, zero volume. Black holes are the ultimate paradox of nature. Objects so dense, so extreme, that the very fabric of space and time collapses into a singularity, a point where the equations of physics themselves break down, where density becomes infinite and volume shrinks to zero, creating a region of space-time from which nothing, not even light, can escape. And yet, despite their apparent simplicity, a point of infinite density, surrounded by an event horizon, the reality of black holes is a labyrinth of contradictions and cosmic mysteries that challenge our very understanding of reality. Because what does it truly mean for something to have infinite density? Density, in its simplest form, is mass divided by volume, and when volume approaches zero, while mass remains finite, the quotient skyrockets toward infinity. But in physics, infinities are red flags, signals that our current models are being pushed beyond their limits. And this is precisely what happens at the singularity of a black hole, where general relativity predicts an infinite curvature of spacetime, an infinite concentration of mass energy into an infinitesimal point, but where quantum mechanics, the theory of the very small, offers no reconciliation, leaving us with a chasm of ignorance at the heart of every black hole, because general relativity is a classical theory, elegant and precise in describing the warping of spacetime by mass and energy. But it knows nothing of quantum uncertainty, of the probabilistic froth that governs particles at Planck scales. And so, when gravity becomes so intense that spacetime folds into itself, creating a singularity, we are forced to confront the fact that our mathematical tools are no longer adequate, that infinity here is not a physical quantity, but a symptom of our incomplete understanding. And yet, from an observational standpoint, black holes behave as if they contain a singularity, with all their mass concentrated into a central point, exerting gravitational influence on surrounding matter, bending light, swallowing stars, and emitting gravitational waves when they collide. Phenomena we have now observed with remarkable precision through instruments like LIGO and the Event Horizon Telescope, which captured the first direct image of a black hole's shadow in the galaxy M87, a haunting orange ring of heated plasma, orbiting a void, and that void, though depicted as a hole, represents the event horizon, the point of no return, not the singularity itself, which remains hidden, cloaked forever by the veil of spacetime, because to any external observer, the singularity is unreachable, inaccessible. a forbidden region where our concepts of space, time, and causality dissolve. And yet its presence is undeniable, for it dictates the behavior of the black hole's gravitational field, a field that is well described by the solutions to Einstein's equations, such as the Schwarzschild solution for non-rotating black holes, the Kerr solution for rotating ones, and the Reissner-Nordström and Kerr-Newman solutions for those with electric charge, each offering a mathematical glimpse into the warping of spacetime, but all converging on the inevitable conclusion of a central singularity where the curvature becomes infinite, where geodesics, the paths followed by objects and light in curved spacetime, terminate abruptly, a geodesic incompleteness that signals the breakdown of predictability. And yet, despite this mathematical singularity, the observable properties of black holes are elegantly simple, described by just 3 parameters: mass, spin, and charge, a remarkable minimalism known as the no-hair theorem, which states that black holes, regardless of their formation history, are fully characterized by these 3 quantities, as if nature erases all other information at the threshold of the event horizon, a process poetically termed the information paradox, because quantum mechanics insists that information cannot be destroyed, yet classical general relativity seems to suggest that anything falling into a black hole is lost forever, a conflict that has spurred decades of debate, from Hawking's proposals of information being encoded in Hawking radiation to the holographic principle, which posits that all information within a volume can be represented on its boundary, suggesting that the information swallowed by a black hole might be stored on its event horizon, much like a hologram. And yet, the singularity itself remains a mystery, a point where space and time become meaningless, where tidal forces grow infinitely strong, stretching and compressing matter into oblivion, a process known as spaghettification, vividly illustrated in the case of stellar mass black holes, where the gravitational gradient between an object's head and feet would elongate it into a thin filament before crushing it into singular oblivion. But even this is a macroscopic description, for at the Planck scale, space-time may no longer be smooth, but a foamy, fluctuating sea of quantum geometry, where the very notion of a singularity might be replaced by something more subtle, perhaps a quantum-corrected core, a Planck-scale remnant, or a bounce leading to a white hole. Speculative concepts explored in quantum gravity theories like loop quantum gravity and string theory, each offering tantalizing glimpses of a reality beyond the singularity, but none yet confirmed, because the heart of a black hole is forever, hidden from direct observation, shielded by the event horizon, beyond which signals cannot escape, leaving us with only indirect probes, gravitational waves from mergers, accretion disk dynamics, and the faint whispers of Hawking radiation, a quantum process by which black holes slowly evaporate, emitting particles due to quantum fluctuations near the horizon, leading, over vast timescales, to their eventual dissolution. Though for stellar mass and supermassive black holes, this evaporation is so slow it is negligible compared to the age of the universe. But for microscopic black holes, it becomes significant, suggesting a link between quantum processes and gravitational collapse, a link that might one day resolve the singularity paradox, revealing that infinite density and zero volume are not physical realities, but mathematical artifacts signaling the need for a quantum theory of gravity. And yet, until such a theory is achieved, we are left with the singularity as a boundary of knowledge, a reminder that even in our most precise theories, there are regions where understanding fails, where infinity creeps into the equations, not as a physical truth, but as a signpost marking the limits of current science. And in this sense, black holes are both triumphs and torments of physics, objects that simultaneously showcase the predictive power of general relativity, accurately describing orbits, gravitational lensing, time dilation, and frame dragging, while also exposing its inadequacies at extreme scales, where quantum effects cannot be ignored. And so, when we say that black holes have infinite density and zero volume, we are stating a consequence of extrapolating classical equations into regimes where they no longer hold, a placeholder for an unknown truth, a mystery wrapped within the very structure of space-time, challenging us to seek a deeper understanding, to reconcile the continuous with the discrete, the geometric with the probabilistic, the smooth curvature of Einstein with the granularity of Planck, and perhaps, one day, through a synthesis of quantum mechanics and gravity, we will unveil what truly lies at the heart of a black hole, not a singularity of infinite density and zero volume, but a new realm of physics, where space and time themselves are reborn. You can't know a particle's speed and location. Exactly. In the world you see, certainty feels natural. A ball has a position, a car has a speed, and at any given moment you can measure both, precisely, simultaneously, without conflict. Yet, at the quantum level, this intuition dissolves, replaced by a strange and fundamental truth of nature. You cannot know both the exact position and exact momentum, speed and direction of a particle at the same time. Not because of technological limitations, not because of measurement errors, but because the universe itself does not allow it. A principle enshrined in the very bedrock of quantum mechanics, known as the Heisenberg uncertainty principle, which declares that the more precisely you determine a particle's position, the less precisely you can know its momentum, and vice versa, a limit not of human ingenuity, but of physical reality, expressed mathematically as Dex. dp h2, where the x is the uncertainty in position, dp is the uncertainty in momentum, and h is the reduced Planck's constant, an unimaginably tiny number, yet one that defines the scale at which quantum effects become inescapable. And though this uncertainty is negligible in the macroscopic world, where Planck's constant is dwarfed by everyday masses and distances, at the scale of atoms, electrons, and photons, it becomes dominant, unavoidable, a defining feature of reality itself. And to grasp this, you must abandon classical notions of particles as tiny, billiard ball-like objects with precise trajectories. Because in quantum mechanics, particles are described by wave functions, mathematical entities that encode probabilities, not certainties, spreading out over space, defining regions where a particle is more or less likely to be found, but never pinpointing a singular, exact location. And this wave-like nature means that attempting to confine a particle to a very small region of space, to sharpen its position, necessarily broadens the range of its possible momenta, because a sharply localized wave packet requires the superposition of many different momentum states, and conversely, a particle with a well-defined momentum has a delocalized, spread-out position, as seen in the classic example of an electron in a hydrogen atom, where its orbit is not a fixed path, but a diffuse cloud of probability, the electron smeared across space, never at rest, never precisely located, and this inherent fuzziness is not a sign of incomplete knowledge, but a reflection of the fundamental nature of quantum objects, leading to profound consequences across physics, chemistry, and even philosophy, as it reshapes our understanding of measurement, determinism, and reality itself. Because Heisenberg's principle is not a statement about the limitations of instruments, but about the limits imposed by nature's very fabric, a fabric woven not from certainties, but from probabilities, where the act of measurement does not merely reveal properties, but defines them, collapsing the wave function from a spread of potentialities into a single outcome, an event inherently probabilistic, never deterministic, a stark departure from Newtonian predictability. And this interplay of uncertainty becomes vividly apparent in phenomena like electron diffraction, where particles exhibit interference patterns characteristic of waves, even when fired one at a time, each electron's path fundamentally uncertain, yet statistically predictable, forming patterns that reveal the underlying wave nature. And in quantum tunneling, where particles surmount energy barriers not by brute force, but through the non-zero probability of existing on the other side, a phenomenon with no classical analogue, enabled by the indeterminacy of position and momentum, and even the stability of atoms owes itself to uncertainty. For if electrons could have perfectly defined positions within atoms, they would collapse into the nucleus under electromagnetic attraction. But Heisenberg's principle forbids such confinement, the uncertainty in momentum providing a quantum pressure that prevents this collapse, maintaining the very structure of matter, and thus, the solidity of the world you inhabit is born not from precision, but from uncertainty, a delicate balance. enforced by quantum rules, and this principle echoes in the zero-point energy of fields, where particles fluctuate incessantly, even in the ground state, never truly at rest. Their positions and momenta are perpetually uncertain, and in the vast expanse of the cosmos. This uncertainty shapes the early universe, where quantum fluctuations, magnified by cosmic inflation, seeded the large-scale structure of galaxies and clusters. The fingerprints of uncertainty writ large across the heavens, and yet, for all its abstract strangeness, Heisenberg's principle is experimentally verified, as seen in the diffraction of electrons, the behavior of cold atoms, the operation of scanning, tunneling microscopes, and the constraints of precision metrology, where even the sharpest measurements must bow to the quantum limits. And while thought experiments like Schrödinger's cat dramatize the paradoxes of quantum measurement, at their core lies this same uncertainty, this refusal of nature to allow complete, simultaneous knowledge of complementary variables, a reflection of the deep mathematical structure of quantum theory, where operators corresponding to position and momentum do not commute, their non-commutation encapsulating the uncertainty principle in algebraic form. And this non-commutation is not a flaw, but a feature, essential to the coherence of quantum theory, ensuring the consistency of probability amplitudes and the unitarity of evolution. And yet, this principle is often misunderstood, conflated with observer effect or measurement disturbance, when in truth, it expresses a deeper truth, that quantum properties do not exist as definite values prior to measurement, but as probabilities, constrained by the inherent limits of knowability, making the very question of a particle's exact position and momentum simultaneously ill-posed in the quantum realm. And this forces a rethinking of reality itself, suggesting that the classical notion of objects with well-defined attributes, existing independently of observation, is an emergent approximation, valid at macroscopic scales, but breaking down in the quantum domain, where entities exist not as sharply defined things, but as clouds of possibilities, governed by a mathematics of uncertainty. And so, when you imagine an electron orbiting a nucleus, do not picture a tiny sphere tracing a predictable path, but a dynamic, probabilistic haze, a shifting cloud whose precise location and momentum are fundamentally intertwined, constrained by the limits of the uncertainty principle. A principle that, far from being a mere technicality, is a profound statement about the nature of existence, a window into the quantum realm where certainty gives way to probability, determinism yields to indeterminacy, and the very fabric of reality pulses with the dance of uncertainty, ensuring that you can never, under any circumstance, know both the exact position and exact speed of a particle at the same time, because the universe itself does not permit it. The universe is expanding faster than light in some areas. The universe is expanding. You've heard this before. A cosmic stretching of space, a gentle drifting apart of galaxies over time. But beneath that calm image lies a startling truth. In certain regions, the universe is expanding faster than light, not in the sense of objects flying through space at superluminal speeds, but because space itself, the very fabric of reality, is stretching in a way that outpaces even light's ability to bridge the growing gaps. A concept that at first feels like a violation of Einstein's cosmic speed limit, yet in truth conforms perfectly to the laws of relativity, not contradicting them, but revealing how profoundly misunderstood the nature of expansion truly is. Because when we say nothing can go faster than light, we refer to objects moving through space, not to the expansion of space itself, which is governed by general relativity and its dynamic geometry, where distances between distant points can increase faster than light, simply because the intervening space is growing, not because the objects themselves are locally exceeding light speed. And this distinction, subtle yet crucial, is the key to understanding why vast regions of the universe are receding from us at velocities greater than c, the speed of light in vacuum, even as local physics remains inviolate, because general relativity does not impose a universal speed limit on the rate at which space itself can expand, only on the relative motion of objects through space at a given location. And this expansion, described mathematically by the Friedman equations derived from Einstein's field equations, dictates how the scale factor of the universe evolves over time. And it is this scale factor that defines the stretching of distances between comoving observers, Galaxies that, though stationary in their local space, find themselves carried apart by the inflating universe, much like raisins embedded in rising bread dough, where it is not the raisins moving through the dough, but the dough itself expanding, increasing the distance between the raisins without requiring them to travel through their immediate surroundings. And similarly, galaxies recede from each other, not because they are flying away through space, but because space between them is stretching, and at sufficiently large separations. This recession velocity exceeds the speed of light, not as a violation of special relativity, but as a natural consequence of general relativity's treatment of expanding spacetime, leading to the concept of a cosmological horizon, beyond which galaxies recede so rapidly that their light can never reach us, because the intervening space is expanding faster than photons can traverse it, placing these regions forever beyond our observational reach, not because their light is too faint, but because the fabric of space stretches the light to infinite wavelengths, rendering it undetectable. And this horizon, often called the Hubble radius, or particle horizon, is not a fixed boundary, but evolves over time as the expansion rate changes, influenced by the universe's energy content, matter, radiation, dark matter, and most importantly, dark energy, whose repulsive effect accelerates the expansion, ensuring that more and more regions slip beyond the cosmic horizon, never to be seen again, a process vividly illustrated in the context of cosmic inflation, the rapid exponential expansion thought to have occurred in the universe's first tiny fraction of a second, where the expansion rate was so extreme that regions of space were pulled apart faster than any signal could traverse, solving puzzles like the horizon problem and laying down the seeds of cosmic structure through magnified quantum fluctuations. And even today, on far grander scales, the same principle persists, with the observable universe bounded by this horizon, a spherical shell approximately 46.5 billion light-years in radius, though the universe itself may be vastly larger, perhaps infinite, or perhaps finite but unbounded, like the surface of a higher dimensional sphere. And in these far reaches, galaxies recede from us at superluminal speeds, their existence inferred from cosmological models, but their light forever denied to our instruments. And as dark energy continues to drive accelerated expansion, this cosmic event horizon will become ever more prominent, shrinking the observable universe, isolating us in a local island of gravitationally bound galaxies, while the rest of the cosmos slips away, not because it moves faster than light in the classical sense, but because the expansion of space itself outpaces light's ability to bridge the gap. And this distinction is not mere semantics, but a profound insight into the nature of space-time, rooted in the principles of general relativity, where the curvature of space and the dynamics of expansion redefine what it means to move, to separate, to recede. And though it feels counterintuitive, it aligns perfectly with Einstein's framework, which permits the metric of spacetime itself to evolve, expanding distances without requiring superluminal travel through local space, preserving causality, upholding relativity, yet revealing a universe whose vastness escapes the bounds of our everyday intuition. And this expansion, while imperceptible, on local scales, where gravitational binding holds solar systems, galaxies, and galaxy clusters together, is relentless on cosmic scales, where the combined effects of dark energy and the sheer scale of space ensure that most of the universe recedes from us faster than light, a reality that challenges our perception of motion, distance, and connection. Because while nothing can overtake a light beam in a local race, the racetrack itself can stretch so rapidly that the distance between runners grows faster than light can cover, and this perspective reshapes how we think about cosmology, transforming expansion from a concept of motion through space to a dynamic growth of space itself, governed not by velocities in the Newtonian sense, but by the evolving geometry of space-time, a geometry that stretches, curves, and evolves according to the distribution of mass energy, as encapsulated in Einstein's equations. And this cosmic expansion, while mind-boggling, is observable, not through the direct measurement of receding galaxies slipping beyond light speed, but through the redshift of their emitted light, the stretching of wavelengths that reveals their recession velocity, a shift that increases with distance, aligning with Hubble's law at modest distances, but diverging at cosmological scales where the expansion rate itself evolves. And through these observations, we piece together the history of the universe's growth, from the rapid inflationary epoch through the decelerated expansion dominated by matter, to the current era of accelerated expansion driven by dark energy, each phase leaving its imprint on the cosmic microwave background, large-scale structure, and galaxy surveys. And yet, for all our measurements, the vast majority of the universe remains unreachable, not because of technological limitations, but because of the fundamental structure of space-time itself, a structure that ensures that in some areas, the universe is expanding faster than light, not as a loophole, not as an exception, but as a feature of the cosmos, a manifestation of the profound difference between motion through space and the expansion of space, a distinction that, once understood, reveals the elegance of general relativity and the true scale of our universe, where faster-than-light expansion is not a violation of nature's speed limit, but a demonstration of the vast, dynamic, and ever-evolving stage upon which the cosmic drama unfolds. Life might be tuned for the universe, or vice versa. It's tempting to look at the universe and believe it was made for us. The perfect balance of forces, the delicate tuning of constants, the narrow window of conditions that allow life, conscious observers to exist and wonder why, as if the universe itself had an intention, a purpose aligned with our emergence. But this intuition, as comforting as it is, demands scrutiny, because beneath the poetic simplicity of "the universe was made for life" lies a profound and unresolved question. Is life tuned for the universe, or is the universe tuned for life? And perhaps more radically, is this dichotomy even meaningful? Or does it reveal more about human perspective than about the nature of reality? Because when we examine the physical constants, the strength of gravity, the charge of the electron, the fine structure constant, the cosmological constant, we find that small deviations in their values would render the universe inhospitable to life as we know it, a fact often cited in fine-tuning arguments, suggesting that our universe is delicately balanced on a razor's edge, where stars can form, planets can stabilize, chemistry can flourish. And yet, this observation raises a critical question. Does this fine-tuning indicate design, necessity, or mere selection bias? Because from a scientific standpoint, there are several frameworks to interpret this apparent precision. One being the anthropic principle, which states, rather bluntly, that we observe a life-permitting universe because only in such a universe could observers exist to notice it, a tautology on the surface, yet a powerful reminder of selection effects, because if countless universes exist, each with different physical laws, only those with the right conditions would host life, making our universe's life-friendliness less surprising, not because it is special, but because we are here to ask. And this concept, while often misunderstood as a philosophical shrug, is supported by theories like eternal inflation and the multiverse hypothesis, suggesting that our observable universe is but one bubble in an infinite cosmic foam, each bubble with its own values of physical constants, some sterile, some chaotic, some nurturing complexity, and we, unsurprisingly, find ourselves in one of the latter. Yet the anthropic explanation, while pragmatic, feels unsatisfying to many, as it seems to sidestep deeper questions about necessity and contingency, prompting alternative views, such as the possibility that life is not the product of a universe tuned to support it, but rather, life is the emergent result of adapting to the universe's parameters, that biochemistry, molecular structures, and even consciousness are not privileged outcomes, but contingent configurations of matter exploiting the available pathways dictated by physical law, that if the universe's constants were different, life might still arise in radically unfamiliar forms. Carbon replaced by silicon, water by ammonia, or structures and processes we cannot yet imagine, constrained not by human-centric notions of life, but by the deeper logic of thermodynamics and information processing, suggesting that life, in a general sense, might be an inevitable phenomenon wherever complexity can self-organize, much like how turbulence arises in fluid dynamics, or crystal structures emerge from cooling solutions. And in this view, life is tuned to the universe, sculpted by its conditions, not the other way around, an evolutionary process writ large across cosmic timescales. And yet, this does not diminish the awe of fine-tuning, Because even if life is a contingent emergent phenomenon, the fact that our universe's constants fall within the narrow band that allows such emergence remains a remarkable fact, one that invites further questions. Why these values? Why this universe? Why any universe at all? And here, theoretical physics enters speculative territory, exploring ideas like the string theory landscape, where 10,500 possible vacuum states give rise to a vast array of potential universes, each with different constants or models where the laws of physics are not fundamental, but emergent properties of deeper pre-geometric realities, where constants arise from symmetry breaking, quantum fluctuations, or boundary conditions of the multiverse itself. And amidst these speculations lies the provocative suggestion that the very act of observing might play a role in defining reality, as hinted by quantum mechanics, where measurement collapses probabilities into definite outcomes, raising the philosophical possibility that consciousness and cosmology are entwined more deeply than we understand, not in the mystical sense of the universe requiring us, but in the formal sense that the emergence of observers is a natural, perhaps inevitable consequence of the universe exploring its own degrees of freedom, maximizing entropy production, or unfolding complexity in accordance with the second law of thermodynamics. And thus, life might be seen not as an anomaly, but as an expression of the universe's tendency toward complexity within locally low entropy environments, a thermodynamic necessity rather than a miraculous exception. And in this framework, the question of tuning becomes less about intentional design and more about statistical inevitability across a sufficiently large and diverse ensemble of universes. Yet even this statistical view does not fully resolve the emotional weight of the fine-tuning argument, because humans are pattern-seeking creatures, wired to ascribe purpose, agency, and meaning to the structures they observe, and the uncanny fit between the universe's parameters and the requirements for life inevitably triggers existential reflection, leading to frameworks like the strong anthropic principle, which posits that the universe must be compatible with conscious life, perhaps suggesting deeper teleological significance, though such ideas often tread the line between science and metaphysics. And in parallel, alternative scientific theories explore the possibility of self-tuning mechanisms, where the values of physical constants are not arbitrary, but the result of feedback processes, cosmic selection effects, or dynamical systems that stabilize within life-permitting ranges, akin to attractors in chaotic systems, though these remain speculative, lacking empirical validation, yet highlighting the rich interplay between cosmology, complexity, and emergence. And regardless of the explanatory framework, the undeniable fact remains: our existence is intertwined with the universe's properties, whether as a product of design, chance, necessity, or self-organization. And perhaps the question itself, whether life is tuned for the universe or the universe for life, reflects a false dichotomy, born from human-centric thinking, because in a relational view of reality, observer and observed, system and environment, life and universe, are not separate entities, but aspects of a single entangled whole, where distinctions blur and questions of tuning become questions of perspective. And in this sense, the universe is neither for life nor indifferent to it, but life is a mode of the universe knowing itself, a local intensification of complexity arising from the interplay of fundamental forces, chemistry and information, a transient but meaningful pattern in the grand flow of entropy. And whether this pattern is unique, common, or inevitable remains one of the greatest open questions in science, yet the very act of asking connects us to the deepest currents of cosmic evolution, where life, consciousness, and the universe are not separate threads, but interwoven strands of the same fabric, shaped by the constants of physics, yet shaping our understanding of those constants in return, making the question of tuning less about privilege and more about participation, less about why and more about how, a dynamic relationship between existence and awareness, where perhaps, in the final analysis, life is not the reason for the universe, nor is the universe fine-tuned for life, but both are manifestations of the same underlying reality, unfolding in concert, co-emerging, co-defining, until the distinctions between life and universe dissolve into a single continuous process of being. Your present is someone else's past. When you look at the stars, you are not seeing them as they are, but as they were. an ancient light traversing the vastness of space, reaching you after years, centuries, even millennia of travel, turning the night sky into a living fossil record, a cosmic time machine where every glimmer is a glimpse into history. And though this idea feels poetic, it is a direct consequence of one simple fact. Light has a finite speed, nearly 300,000 kilometers per second, an astonishing velocity by human standards, yet not instantaneous, meaning that every image you perceive, every photon that touches your retina left its source in the past, whether from the screen before you nanoseconds ago, or from a distant galaxy billions of years away, making the present you experience a carefully curated tapestry of delayed signals stitched together by your brain into a seamless now. And yet, this now is an illusion, a local, subjective construct that differs from place to place, observer to observer, because while you experience this moment as present, for someone else, it is already the past, a lagging echo of an event long gone. And this dissonance between perception and reality is not limited to the distant cosmos, but permeates every interaction, every observation, every act of seeing, because even on the scale of Earth, the finite speed of light imposes delays, infinitesimal but real, so that when you look at a friend across a room, you are seeing them as they were nanoseconds ago. And this delay scales with distance, transforming into seconds for lunar reflections, minutes for solar light, and years for interstellar beacons. Yet the most profound realization emerges not from the smallness of these delays, but from their inevitability, from the fact that there is no absolute now that stitches the universe together, no cosmic present that synchronizes all events, because relativity teaches us that simultaneity is relative, that what is now for you is then for someone else, depending on their location and motion. And this isn't a philosophical abstraction, but a fundamental feature of space-time encoded in the Lorentz transformations, which reveal how time dilates and contracts based on velocity and gravity, ensuring that observers in different frames will disagree on what events are simultaneous. And thus, the very notion of a shared present dissolves, replaced by a tapestry of interwoven pasts, presents, and futures, all dependent on perspective. And this becomes starkly evident when considering distant galaxies receding at relativistic speeds due to cosmic expansion, where light emitted now may never reach us, and light we receive today may have left its source before Earth even existed, creating a universe where your present is perpetually someone else's past, and even your future light will be someone else's history, a continuous layering of time slices across space, blurring the boundaries between what is and what was. And this phenomenon is not confined to the vast scales of cosmology, but manifests in subtle ways in daily life, through the finite time it takes for light to propagate, for signals to transmit, for information to travel. And while these delays are negligible for most practical purposes, they reveal an inescapable truth. Perception is always retrospective, a reconstruction of past events into a coherent narrative of now. And the further you look, the deeper into the past you peer, making every act of observation an act of historical archaeology, whether gazing at the moon's light from a second ago or catching starlight from centuries past. And this perspective reshapes your understanding of causality, of connection, of presence itself. Because if there is no absolute present, if every point in the universe operates on its own localized timeline, then what does it mean to be in the moment? Are you ever truly experiencing reality as it is? Or are you perpetually chasing its trailing echoes, forever a few steps behind the unfolding now? Relativity suggests the latter, and yet, this does not diminish your experience, but rather enriches it, revealing the profound complexity of space-time, where light cones define the structure of causality, separating events into past, present, and future, not globally, but locally, ensuring that your observable universe is a dynamic, evolving bubble, where every photon is a messenger from the past, every shadow a lingering imprint of prior moments, and even your interactions with others are shaped by these constraints, as signals transmitted, received, and processed introduce unavoidable delays, making every conversation, every glance, a dance of temporal echoes, synchronized not by absolute simultaneity, but by the fluid choreography of relativistic constraints. And in this light, the universe becomes a grand mosaic of intertwined timelines, where the concept of now is fragmented, subjective, dependent on position and motion, and yet, within your frame of reference, this illusion of now remains robust, a testament to the brain's remarkable ability to integrate delayed inputs into a cohesive experience, masking the inherent lag of perception, yet never eliminating the fundamental truth that every sight, every sound, every sensation is a delayed report from the past, and this extends to every level of existence, from the subatomic interactions governed by quantum uncertainty to the grand ballet of galaxies drifting apart, each governed by the same inviolable limit: the speed of information transfer, ensuring that no signal, no influence, no causal effect can outpace light in a vacuum, anchoring the structure of space-time and defining the boundaries of what can be known, what can be influenced, and what remains forever beyond reach, making your present, inevitably, someone else's past, and perhaps, simultaneously, your own future in another's timeline. Depending on the paths light has taken, the frames of reference involved, and the relativistic shifts that sculpt the perception of time, transforming the simple act of seeing into a profound intersection of physics and philosophy, where every glance is a communion with history, every observation a dialogue with the past. And yet, this interconnectedness does not fragment reality, but weaves it into a cohesive whole, where the flow of information binds observers into a shared, though asynchronous, fabric of existence. A reality where your now is always a little late, always playing catch-up, and yet always perfectly synchronized within the bounds of physical law, making the universe not a static backdrop, but a dynamic, ever-evolving web of causally connected events, each observer anchored in their own light cone, each perspective valid, yet incomplete. And this realization invites a humbling shift in perspective, reminding you that presence is a local phenomenon, defined by proximity, constrained by the speed of light, and sculpted by the relativistic dance of space-time, ensuring that while you experience a seamless now, the universe itself is a sprawling mosaic of layered pasts, where your present moment is perpetually someone else's history, and in turn, your light, your influence, your very existence becomes a ripple propagating outward, destined to become the past of countless distant observers, if only they could ever see it. The stronger the gravity, the slower the time. You've heard that time is constant, that seconds tick away with mechanical precision, that the universe marches forward in a rhythm as steady and absolute as a metronome. But this, like so many comforting illusions, shatters under the weight of reality, because time is not constant, not universal, not immune to the forces that shape space itself. And nowhere is this more apparent than in the presence of gravity, where the fabric of space-time bends, curves, and warps under mass and energy, slowing the passage of time in a phenomenon known as gravitational time dilation, a consequence of Einstein's general relativity that reveals a truth so profound, so quietly unsettling, that it forces you to reconsider what time even is. Because in regions of stronger gravitational potential, time runs slower relative to regions of weaker gravity, not as a trick of perspective, but as an intrinsic property of space-time geometry, encoded in the equations that govern the universe, ensuring that a clock near a massive object, be it a planet, a star, or a black hole, ticks more slowly than an identical clock farther away. And this effect, though negligible in daily life, becomes measurable with sensitive instruments, as demonstrated by experiments like the Pound-Rebka experiment in 1959, which detected time dilation due to Earth's gravity over a height difference of mere 22.5 meters, and more dramatically, by the Global Positioning System, GPS, whose satellites, orbiting high above the planet's surface, experience weaker gravity and therefore faster time relative to ground-based clocks, requiring continuous relativistic corrections to maintain navigational accuracy. And yet, while these technological adjustments bring general relativity into the realm of the everyday, the true grandeur of gravitational time dilation reveals itself in extreme environments, near neutron stars where matter is crushed into degenerate densities, near black holes where space-time folds into singularities, where the gravitational potential grows so intense that time itself appears to freeze from the perspective of a distant observer, as exemplified by the event horizon, the boundary beyond which nothing, not even light, can escape. And yet, for an infalling observer, time continues to flow normally, unimpeded, creating a paradox of perspectives where the same event, a fall into a black hole, unfolds differently depending on one's vantage point, with the distant observer watching the infaller approach the horizon asymptotically, never quite crossing, the image redshifting, fading, slowing, until it appears frozen in time, while the infaller experiences a finite, inevitable plunge toward the singularity, illustrating the profound relativity of time in curved space-time. And this interplay between gravity and time is not an abstract mathematical artifact, but a tangible, measurable reality, one that governs the aging of clocks, the synchronization of systems, the flow of causality itself, because in the presence of mass, space-time tells matter how to move, and mass tells space-time how to curve. A mutual relationship that defines the geometry of the universe, where time is no longer a separate backdrop, but a dynamic participant, stretched and compressed by the very existence of matter and energy. And this leads to startling implications, such as the realization that you, standing at sea level, age more slowly than someone living atop a mountain, not by much, perhaps nanoseconds over a lifetime, but measurably so. And this divergence grows with gravitational strength, becoming dramatic near compact objects, and in the theoretical scenario of a civilization existing near the event horizon of a supermassive black hole, the difference would be profound, with years passing for the distant universe while mere hours unfold locally. A concept famously dramatized in science fiction, but grounded in the hard mathematics of general relativity. And yet, beneath these numerical predictions lies a deeper philosophical shift, because if time flows differently for different observers, then the notion of a universal now dissolves, replaced by a patchwork of local times, each defined by its position in the gravitational landscape. And this reframes your understanding of simultaneity, of cause and effect, of what it means to experience the present, because time is not an immutable current flowing uniformly through the cosmos, but a malleable dimension shaped by gravity's hand, ensuring that every observer's passage through time is uniquely sculpted by their position in space-time. And this becomes even more striking when considering the expanding universe itself, where gravitational potentials vary across cosmic structures, from dense galaxy clusters to vast intergalactic voids, subtly influencing the flow of time in ways that, while imperceptible to us, shape the evolution of cosmic structures. And as you contemplate this, it becomes clear that time is not a universal metronome, but a local phenomenon, woven into the very shape of space. And thus, every experience of time is an experience of place, of gravitational context, of space-time curvature. And this understanding forces a re-evaluation of fundamental concepts, as it suggests that the passage of time is not a property of a distant, detached clockwork universe, but a dynamic, evolving process intimately tied to the matter and energy that inhabit space. And in this sense, gravity does not merely pull on objects, it pulls on time itself, stretching, slowing, sculpting the river of moments into eddies and pools, where some regions flow quickly and others sluggishly. And in the extreme limit, as mass and energy converge towards singularities, time itself can halt from certain perspectives, creating boundaries beyond which events are forever sealed from the external universe. And yet, these are not edges of space, but edges of time's flow, revealing that space and time are not separate entities, but facets of a single unified space-time fabric, whose curvature dictates the experience of motion, causality, and existence itself. And thus to say that the stronger the gravity, the slower the time, is not merely to state a physical effect, but to acknowledge a profound truth about the nature of reality, a truth that dissolves the comforting illusion of universal time and replaces it with a dynamic, curved, and relative landscape where every observer traces their own unique path through the fabric of space-time, shaped by the gravitational contours of the cosmos. And within this landscape, your experience of time is a local phenomenon, tethered to the curvature beneath your feet, subtly influenced by the planet you stand on, the galaxy you orbit within, the structures that define your cosmic neighborhood, all contributing to the intricate ballet of gravitational time dilation that ensures that time, far from being an absolute, is as fluid and contextual as space itself. the universe is mostly dark matter and energy. The universe you see, the stars that dazzle, the planets that orbit, the galaxies that swirl across the vastness of space, feels immense, overwhelming in its scale and beauty. Yet beneath that splendor lies a humbling, even unsettling truth. Everything you can see, touch, measure, or detect with light, every atom of your body, every molecule of air, every shimmering nebula and blazing quasar, accounts for less than 5% of the universe's total content, with the overwhelming majority of existence hidden in forms we cannot see, cannot directly detect, yet whose gravitational fingerprints are indelibly stamped across the cosmos. A realm dominated not by familiar matter, but by two enigmatic components: dark matter and dark energy, which together make up approximately 95% of the universe's mass energy content, reshaping our understanding of reality, forcing us to confront the fact that what we consider normal is a mere afterthought in the grand ledger of the cosmos, because dark matter, making up roughly 27%, does not interact with light or electromagnetic forces, remaining invisible to telescopes, yet revealing itself through gravitational effects, holding galaxies together, bending light through gravitational lensing, and forming the cosmic scaffolding upon which visible matter accumulates, while dark energy, accounting for a staggering 68%, acts as a repulsive force driving the accelerated expansion of the universe, a mysterious property of space itself that defies our intuitions about gravity and attraction. And together, these dark components constitute the unseen architecture of reality, shaping the universe's large-scale structure, its past, its present, and its ultimate fate. And this realization did not come easily, but emerged from the convergence of multiple lines of evidence, starting with the observation of galaxy rotation curves by Vera Rubin in the 1970s, who found that stars in the outer regions of spiral galaxies orbit at velocities that cannot be explained by the visible mass alone, suggesting the presence of an unseen mass providing additional gravitational pull, leading to the postulation of dark matter halos enveloping galaxies, and further supported by gravitational lensing measurements, cosmic microwave background anisotropies, and large-scale structure surveys, each revealing a universe where visible matter is insufficient to account for the observed gravitational dynamics. While dark energy's existence was thrust into the spotlight in the late 1990s, when observations of distant Type Ia supernovae revealed that the universe's expansion is not slowing down, as expected from gravitational attraction, but accelerating, a discovery so profound it earned a Nobel Prize and demanded the inclusion of a cosmological constant or an equivalent dark energy component in our cosmological models, altering the Friedmann equations and reshaping our projections for the universe's long-term evolution, suggesting a cosmos that will continue to expand, possibly forever, growing colder, darker, and more isolated, with distant galaxies receding beyond our observable horizon, driven by the relentless influence of dark energy. And yet, despite their profound impact on cosmic dynamics, the true nature of dark matter and dark energy remains elusive, with dark matter candidates ranging from weakly interacting massive particles, WIMPs, to axions, sterile neutrinos, and even modifications to gravity itself, such as MOND, modified Newtonian dynamics, though none have yet provided conclusive evidence. While dark energy's essence might be a cosmological constant, an intrinsic energy density of the vacuum, or a dynamic field akin to quintessence, each model grappling with the observational data, yet falling short of a definitive explanation. And this profound ignorance at the heart of cosmology forces us to confront the limits of our knowledge, acknowledging that the universe, in its vastness, operates through mechanisms that transcend our current theories, and that our perception of reality is constrained not just by the limitations of our instruments, but by the very structure of the cosmos, which hides the majority of its content from direct detection, offering only gravitational whispers and cosmic echoes as clues. Yet these whispers are powerful, guiding our understanding of cosmic evolution, informing simulations of galaxy formation, explaining the large-scale filamentary structure of the universe, where dark matter forms vast cosmic webs, attracting baryonic matter into galaxies and clusters, while dark energy dictates the universe's expansion history and future trajectory. And this interplay between dark matter and dark energy defines the cosmic balance, a balance that determines whether the universe will expand forever, halt, or collapse. Though current data strongly favor perpetual acceleration, a scenario that paints a future of increasing isolation as galaxies recede beyond visibility, stars burn out, and the universe approaches thermodynamic equilibrium, a fate shaped not by the luminous matter we see, but by the dark components we infer, making the realization that the universe is mostly dark matter and energy not just a numerical fact, but a philosophical shift, forcing us to reevaluate our place in the cosmos, recognizing that our existence is a marginal phenomenon, a byproduct of conditions shaped by forces and substances we cannot yet comprehend, yet whose influence permeates every aspect of cosmic structure and dynamics. And this humbling perspective challenges anthropocentric views, inviting a broader understanding of existence, where visibility is not the measure of importance, and where the unseen defines the structure of the seen, a universe where light, though beautiful, is but a tracer of deeper, darker currents. And in this realization lies a profound lesson, that the universe is not obliged to be accessible to human senses, that reality extends far beyond what we can observe, and that true understanding requires embracing the unknown, the invisible, the dark, as essential components of existence, shaping the cosmos in ways we are only beginning to grasp, ensuring that the quest to understand dark matter and dark energy is not merely an academic pursuit, but a journey toward comprehending the very fabric of reality itself. Some theories don't require time at all. Time feels inescapable. It orders your thoughts, defines your memories, measures your experiences, ticking relentlessly from past to present to future. A river carrying you forward whether you swim or not, yet beneath this deeply human perception of time lies a startling truth. Some of the most profound theories in physics suggest that time, as you experience it, may not be fundamental at all, but an emergent illusion, a convenient parameter arising from deeper, timeless laws, where the universe exists as a complete, static entity, unchanging in its totality and what you perceive, as the flow of time is merely your subjective navigation through this timeless reality. Because when you strip away the layers of human perception, the mathematics of fundamental physics often reveals equations that make no explicit reference to time, such as the Wheeler-DeWitt equation in quantum gravity, which seeks to unify general relativity and quantum mechanics, yet conspicuously lacks a time parameter, implying a universe where the concept of before and after is not fundamental, but arises from relational configurations of matter and energy, a view further echoed in the timeless formulation of quantum cosmology, where the universe is described by a wave function that encompasses all possible states simultaneously, with no preferred temporal ordering. And this radical perspective challenges the very foundations of how you understand existence, because, in everyday life, time feels as real as space. Yet in the realm of fundamental physics, time behaves differently, lacking the spatial dimension's symmetry, flowing in one direction, seemingly irreversible, a feature not of the fundamental equations themselves, but of thermodynamic conditions, where the arrow of time is intimately tied to entropy, the measure of disorder, suggesting that the unidirectional flow of time is a macroscopic phenomenon, emerging from the universe's initial low-entropy state, rather than a fundamental property of reality. And this thermodynamic arrow gives rise to the psychological arrow, the way you remember the past but not the future, the way cause precedes effect. But if the universe's fundamental laws are time-symmetric, with no preferred direction, then time's arrow is not built into the laws themselves, but is a contingent feature of initial conditions, a viewpoint, supported by models like Julian Barber's timeless physics, where reality is a vast configuration space of possible nows, each representing a complete timeless snapshot of the universe, with the illusion of time arising from the structure and relationships between these configurations. Much like frames of a film reel exist simultaneously, yet motion is perceived only when they are sequenced, and in this view, your experience of flowing through time is akin to moving through successive configurations with no objective flow inherent to the universe itself, raising profound questions about the nature of change, causality, and existence, and even in general relativity. Time is not a universal, absolute entity, but a dimension intertwined with space, its measurement depending on the observer's frame of reference, velocity, and position in a gravitational field, suggesting that time is more a measure of change than a fundamental backdrop. And this relational view gains further support in approaches like Carlo Rovelli's loop quantum gravity, where time emerges from correlations between evolving quantum states, with no need for a global, external clock. And even in string theory, time emerges as a parameter from deeper structures, with dualities blurring distinctions between spatial and temporal dimensions. And these theories collectively challenge the classical Newtonian notion of time as an ever-flowing river, replacing it with a landscape where time is either absent or emergent, not fundamental, but a derivative concept arising from entanglement, correlations, and thermodynamic gradients. And this reimagining of time invites profound philosophical implications, forcing a re-evaluation of concepts like free will, determinism, and the nature of reality itself. Because if the universe is fundamentally timeless, then the present is not a moving slice of a flowing timeline, but a particular configuration within a static whole, with all possible configurations existing timelessly, making change a matter of perspective, not a fundamental process. And this view resonates with the block universe interpretation of space-time, where past, present, and future all coexist within a four-dimensional structure, with the passage of time being an emergent, observer-dependent phenomenon. And even more radical ideas, such as causal set theory, propose that space-time itself emerges from a discrete set of causally related events, with time arising from the partial ordering of these events, not from a continuous temporal dimension, further suggesting that time, as a smooth parameter, is a macroscopic approximation, not a fundamental entity. And this perspective aligns with the holographic principle, which posits that the information, content of a volume of space can be represented on its boundary, leading to formulations where time is emergent from entanglement patterns on lower dimensional surfaces, hinting at a reality where space-time itself is a derived, emergent phenomenon, not a fundamental backdrop. And this shift from time as fundamental to time as emergent reframes cosmology, quantum mechanics, and even consciousness, suggesting that the sensation of temporal flow is a cognitive construct, a narrative imposed by minds evolved to process causally connected events in a world with an entropic gradient. Yet at the most fundamental level, the universe exists in a state where time, as you understand it, does not exist, and what you experience. As the passage of time is the unfolding of correlations within a timeless whole, a profound realization that challenges not only scientific paradigms, but also existential perspectives. Because in a timeless universe, the notions of birth, death, and progression are reframed as particular configurations within a vast, static possibility space, where the flow of time is an emergent story, not an intrinsic property and understanding. This does not diminish the reality of experience, but enriches it, offering a deeper comprehension of how complex, temporal phenomena arise from atemporal foundations, ensuring that while time may not be fundamental, your experience of it remains profoundly real within your local, emergent frame, a testament to the intricate dance between the deep structure of reality and the narratives constructed by conscious observers, the illusion of stillness. You're always moving, even when you feel stuck. They told you that movement defines progress, that to go anywhere, you have to move your feet, shift your weight, leave something behind, that forward motion is visible, measurable, purposeful, and that stillness is the absence of travel, a kind of stagnation, a refusal of motion. But they were wrong, or perhaps just telling a half-truth, because you are always moving, even now, even sitting still, even when you feel paralyzed by doubt or locked in the present like a stone sunk in mud. Because whether you want to or not, whether you notice or not, whether your mind has caught up or not, you are traveling through time, inch by inch, second by second, moment by moment, in a direction that cannot be reversed, cannot be paused, cannot be exited. Because time, unlike space, is a corridor with no door behind you, no windows to crawl out of, no off switch to press. And even when your body is motionless, even when your thoughts are quiet, your molecules tick forward, your cells age, your memories pile up in layers you don't feel being added. And your life, always, always, moves relentlessly forward. And this truth, this inescapable truth, is so obvious, we almost never look at it, never sit in it, never feel its full weight. Because to feel it is to realize that you are not simply in time. You are on it, riding it like a current, like a wave you didn't ask to surf, and that you have been riding it since before you had language, since before you had memory, since before you even knew what it meant to be, and that now, today, here, this very breath, this very heartbeat is perched on the knife edge of now, with everything behind you fading into memory and everything ahead of you evaporating into uncertainty. And yet the motion never stops, and that motion is time, and you are its passenger. And this makes you ask, what does it mean to move without moving? To be carried by something you can't touch, can't pause, can't negotiate with? And the answer is not just scientific, it's existential. Because if time is something you move through while sitting still, then movement itself is not a function of your will. It is something imposed upon you, something you are born into, something that carries you forward, even when your body resists. And that means you are always changing, even when you don't feel like you are, even when your routines are rigid and your world is small and your thoughts are repetitive and your life feels like a paused frame in a film everyone else is watching. But it isn't paused, not really, because even in stillness, your cells are replicating, your telomeres shortening, your organs aging, your brain laying down memory traces, and time is slipping past you like wind against your face in a moving train. And that train doesn't stop, doesn't slow, doesn't ask permission, and that's terrifying. But it's also beautiful, because it means that you are never truly stuck, never truly frozen, never truly the same from one moment to the next, even if your mind convinces you otherwise. And maybe this is why grief softens with time, why pain dulls, why wounds close not just from medicine, but from minutes, from hours, from the slow, passive balm of being moved through time, whether you want to be or not. And maybe that's why hope is even possible, because you are never where you were, even if it looks the same, even if the room hasn't changed, even if your reflection still blinks back the same familiar weariness. You have moved, and are moving, and will keep moving. And this is not metaphor, it is physics, it is biology, it is the structure of the universe, in which time is not just something that happens. It's something you are inside, a dimension as real as length and width and depth, and you, just by existing, just by breathing, are moving through it at the speed of 1 second per second, always forward, always aging, always becoming. And this turns the simplest moment, sitting in a chair, lying in bed, waiting in traffic, into something profound, because stillness becomes an illusion, and every pause is secretly motion, and every breath is a tiny voyage. And now you begin to understand why memory feels like time travel, why music collapses time, why scent can pull you years into the past with a single molecule. Because time is not just linear, it is layered, and you are not only moving through it, you are made of it, woven from durations and delays, and your past selves are not left behind but carried within you, echoes vibrating in the folds of your brain, in the posture of your spine, in the tone of your voice when you say, "I'm fine," but mean, "I miss the person I was 5 years ago." And all of it, keeps moving forward because you are time. And to live is to pass through yourself again and again, a procession of versions, each shaped by the moment before, and none of them lasting forever. And if you let that in, fully, without flinching, you begin to see stillness differently, not as stagnation, but as anchoring, a moment where you can observe the motion, where you can become conscious of the ride, and maybe even choose how to sit in the train, even if you can't change its direction. And that choice, that awareness, that acceptance of motion inside stillness is power. Not the power to stop time, but the power to meet it, to be in it, to not waste it wishing you could reverse it. And now you understand that nostalgia, that ache for the past, is just your body recognizing that it has moved. And that memory is a kind of phantom limb for a version of yourself that no longer exists, but once sat right where you are now, thinking different thoughts, believing different things, hoping different hopes. And maybe you can honor that version, love them, grieve them, but not return to them, because you are already past them, already ahead, already in a place they never reached. And now the question becomes, what will you do with the motion you're in? What will you build while time carries you? What will you notice? What will you forgive? What will you no longer delay? And this changes everything, because now procrastination isn't laziness. It's a gamble that you'll get more time later, but there are no guarantees, and the train doesn't wait. And stillness is just a disguise time wears when it wants to move quietly. And that silence you feel, it's not emptiness. It's the sound of the universe moving you through a dimension you can't see but are made of. And you are not watching the clock. You are the clock, ticking forward, in heartbeat and thought and breath. And even as you read this, you are not the same person who began the sentence. You are newer, older, further along, further away from birth, closer to death, more refined, more eroded, more real, more human. And you don't need to fear that. You need to notice it. To stand still and realize you are moving. To lie still and realize you are growing. To be still and realize that time is not something happening to you. It is something you are happening through.